temperature. Let me introduce our first speaker today. It's Chris Fryer from Los Alamos, and he's going to speak about probes of the progenitors, engines, and physics behind stellar collapse. The stage is yours, please.
And you can hear me well and see my slides? And that's a yes. So I'm talking about the physics of supernova and what we know about it and what observations are helping us understand that physics. And I just have some pictures of, I'm from Los Alamos National Lab. On the left is a picture of the lab. On the right there's a ski hill 5 miles away. This is skiing down that ski hill. This ski hill was founded by Hans Bethe. He's one of the initial people that helped form this into a ski hill. And there's also a lot of Indian ruins in Los Alamos area. So if you ever want to visit, contact me and we can set up a visit. So what I wanted to talk about is core collapse supernova and what we know about them then. The idea is that these are explosions that happen at the end state of massive, at least some massive stars. The proposal that Zwicky proposed in 1934 for the energy for this violent explosion was the collapse of a massive star down to a neutron star. So they had just realized what a neutron was in the early 1930s, and Zwicky almost immediately proposed, well, a massive star might eventually collapse down to it because it can't support itself. It will collapse down from this iron core down into essentially a star made out of neutrons. So you'll get electron capture on the protons, and that the potential energy release is going to drive the explosion. And definitely there's enough potential energy there. But it was all, kind of hand wavy theory. People were making more and more sophisticated models, doing more and more detailed calculations, but it was all theory really to try to explain these objects until 1987. And in 1987, we had a supernova go off. It was in the Magellanic Cloud, so it was nearby. We had a number of detectors. We actually had seen the progenitor prior to collapse. So on the right here is Sanduic -69202, which is the progenitor of this explosion. And then we saw the explosion. Well, the way we saw the progenitor is we saw the explosion, then went back to images of the Magellanic Clouds and pulled out the progenitor. So this really made a revolution in our models of core collapse supernova. It confirmed that it was something that was a collapse down to a compact object because we detected neutrinos. So we had a burst of neutrinos. It's pretty hard to make that burst of neutrinos from anything but the collapse down to some kind of compact object. We observed the progenitor star, so we knew it was getting produced from the end state of a massive star. But it had brought a lot of questions as well. So on the right here is the neutrino observation. Had a lot of questions that we didn't understand. One was the progenitor was not a red supergiant. It was a blue supergiant. So it wasn't what we expected for the progenitor. And I'll talk about some of these in more detail. The gamma rays that appeared way earlier than we thought they would appear. And I'll tell you why we thought they would appear later. There were a whole bunch of, the lines were more redshifted than we expected them to be. We expected the explosion to be moving at us, the brightest material moving at us, and we would see these blue shifted lines. So we had a number of observations that we just didn't understand. And that really spurred on new models for the engine behind core collapse supernova. So let me just go into detail about the one observation that I mentioned before on the gamma rays arriving earlier than we thought they would. So the gamma rays from supernova, we expect them to come from the decay of radioactive nickel. So nickel 56 is produced right near that, the star collapses down to a neutron star. Right above that neutron star surface, we get conditions that are extremely hot. And we expect these high temperatures to put this material into nuclear statistical equilibrium, and it's going to take whatever's falling in, so it's a silicon shell, and it's going to take that silicon shell and burn it up to nickel 56. And we'll get a whole bunch of nickel 56 right near the center part of, just above that protoneutron star. The explosion then moves out. You end up, and by hook or crook, we're going to get energy from that, the potential energy released. We're going to drive an explosion. But we expected that explosion to be the nickel that's made down near the bottom to be the slowest moving ejecta, and it's covered by this star of material. So we didn't expect to see the gamma rays until it got diffuse enough that the gamma rays could leak out. So initially, the gamma rays from these decaying nickel atoms are just getting absorbed by the outer envelope of the star. So Phil Pinto and Stan Woolsey had a set of models for what the gamma rays should look like, and those models are the solid lines in this diagram, and the diagram is going through time in the supernova. So the top left is 150 days, 200 days in the middle left, 250 days later in the left bottom, and then in the top right is 300, then 500, and then 700 as I go down on the right. And so what they expected was around 250 days, the nickel starts to get into diffuse enough material that we can see the gamma rays. So the gamma rays are starting to come out, and then you're going to peak around 300 days, and then slowly as you run out of nickel, the nickel decays down to cobalt and then to iron 56. As you run out of the nickel and cobalt decay lines, you expect it to just dim and go away. What they saw was at around 150 days, we were already seeing some nickel observations, and then by 200, we had a bright gamma ray signal. So earlier than we expected. What almost everyone interpreted this as being is we needed some kind of mixing in the supernova explosion. So we needed some kind of asymmetry, and asymmetries have played a huge role in our understanding of the supernova explosion. And I'm going to go through just a little bit of the evidence that we had for asymmetries. One was this early emergence of the gamma ray lines. Another was the lines were broader than we expected for the iron. So this is that, again, the nickel is decaying to cobalt and then to iron. The iron lines, we would expect that material to be moving slowly, and it is actually moving fast because we see it in the broadness of the iron lines. So one model that people did is they looked at some kind of mixing in the explosion as the explosion moved out. So you take a spherically symmetric explosion and move it through the star and look at the mixing there, and they say, can we explain that breadth in the iron lines? So that's one of the asymmetries that we tried to explain, and it wasn't enough. So it couldn't just be that you had a spherically symmetric explosion going through and mixing, and at least from the simulations. We also saw broad gamma ray lines, and they were redshifted. So the lines were not, it wasn't just that the lines were broad, it was that they were redshifted. So it was like that material is moving away from us. So that had some clues to the asymmetries. We see asymmetries, and this is an interesting story because I'm using something that looks like a jet-like structure in these, the iron and the silicon. We see asymmetries in supernova remnants. So there was something telling us that supernova remnants also were showing us that there was something asymmetric about the explosion. Now, in this case, for this remnant, the asymmetry can be either in the explosion itself, or it can be something that's asymmetric in the surroundings. So you have to, when you're seeing this data, you have to actually somehow interpret it and figure out which part of, how you are using that information to constrain your models. Other evidence for asymmetries are the kicks that we see in neutron stars and pulsars. So the fast velocities in pulsars also say that you must have some kind of asymmetry in the explosion. And what this led the theorists to start looking at was it cannot just be that the star has asymmetries in it and the explosion, mixing in the explosion is driving these asymmetries. It has to be something asymmetric in the explosion. And Herant et al. In 1992 started to study asymmetries in the explosion by looking at convection right above the protoneutron star. So this is really early calculations where they've had an inner boundary that's supposed to be the protoneutron star. And what they realized is after the star collapses and bounces, so it collapses down to a neutron star, there's a bounce as the neutron star suddenly, the neutron degeneracy pressure, nuclear forces halt the collapse. There's a bounce, and that bounce shock, it stalls, but it leaves behind a profile that's unstable to convection. And so they found that they would develop convection right above the protoneutron star surface. And in 1994, Herant et al. Did a calculation where they followed the star from collapse to bounce. That convection then was able to help drive an explosion, and they drove an explosion. So in 1994, they said, this is not only, may help us with explaining the asymmetries we see, but it also is showing us how do we get that potential energy that's released and be efficient at driving an explosion. So this mechanism, shortly there, about 10 years later, we were able to do the same calculations in 3D. So this is a plot of a figure of a three-dimensional explosion, a slice of a three-dimensional explosion, where the colors are coding the entropy. So you see red is high entropy material that's rising bubbles, and the blue or purple material is low entropy material that's falling in inflows. And the arrows are detecting the velocity. So what this is the very core of this neutron star. So it's the inner, of this collapsing star. So it's the inner 300 kilometers. The blue center is this protoneutron star that formed as we collapsed down. The iron core collapsed down to this neutron star and releases all this potential energy. The rest of the star is still falling in. So in the outer layers, you see this blue low entropy material falling in, and it's falling in at nearly the free fall velocity onto this protoneutron star that has bounced and left behind this convective flow. And then you see the convection that's developing. So we in early 2000s, we had already started running three-dimensional calculations. In the last 2 decades, we have been doing increasingly sophisticated models with better neutrino transport, better physics for the neutrino cross sections, better equations of state, higher resolution, including magnetic fields. So people have been studying this model, but we have come out with a kind of standard paradigm for what I would call normal supernova. Most normal supernova look to be produced by this kind of convective enhanced explosion where the material falls in, it collapses, it bounces, then convection starts to drive motion right above the protoneutron star. And what this does is it allows us to there's a lot of heat in this protoneutron star that's leaking out through neutrinos. It captures this energy and then converts it from this thermal energy to a kinetic energy of convection until it can blow off the star. And so this is kind of the model that everyone is studying. They'll argue about the details, but at this point, most groups are getting explosions with this full multidimensional model with neutrino physics put in. What this model did was it helped us explain those redshifted lines. The explanation is that you went to very low mode convection, and there's lots of different kinds of convective instabilities you can get, but in all of these cases, if you can go to low mode convection, you can get a strong unimodal explosion that goes off in one direction. And what we believe happened with 1987A is we had a strong explosion and it went off in one direction. It's moving away from us. It's moving away at some angle from us, and that causes the redshifted line. So here is a plot of an explosion where the red is the nickel. And so what happened was the explosion is going in one direction. And if you were looking toward it, you would see blue shifted lines. But if you're looking at some angle away from it, you can actually see red shifted lines. So we think that the explosion from 1987A had a dominant mode that was moving away from us. and that that would explain that the redshifted lines we saw in both the gamma ray from the nickel decay and the iron lines. But we went beyond just explaining existing observations. We started to make predictions for other observations. And one of them is, if this convective engine is right, you would expect the innermost material to be asymmetric and have kind of bubbles of material moving out. And the only way to probe this is either looking at the nickel 56 or looking at titanium 44, elements that are produced deep down in that core. So you need to look at the elements that are produced in the core, because the problem with looking at the outer material is that it's affected by the environment it's blowing up into. So you don't know whether the explosion features you're seeing are coming from the asymmetries in the star or the stellar winds, the circumstellar material, or the explosion itself. But if I look at the innermost ejecta, I'm actually looking at asymmetries in the explosion. And in the case of supernova remnants, this is how you would study it. And the NuSTAR satellite went and looked at the titanium 44 that was produced in the core of this Cassiopeia A supernova remnant. And it looked at what's its distribution. And that's the scion material here. And you can see that it's producing kind of asymmetries in the explosion, and we attribute that to this convective engine. And they, the NuSTAR satellite went and they measured these are the decay lines, the gamma rays from, or hard X-rays from the decay lines of titanium 44, and they could look at different material and observe those decay lines. So they actually have a nice 3D map of what these asymmetries look like. So that's one prediction of the model that then was confirmed by observations. Another prediction was that that under this convective engine, it gets harder and harder to drive explosions as you increase the mass of the progenitor. And that's only if mass loss removes all the mass from the star, and we expect that for very high metallicities, then you can explode even a 50 solar mass star if it ends its life as a 3 solar mass star. But if mass loss keeps the core fairly compact, we expect it to be hard to drive explosions from more and more massive stars. And in 1999, we actually argued that above about 25 solar masses, we wouldn't get very many explosions. And at the time, observations were saying the opposite. Observations were saying, there was several observational papers looking at supernova light curves arguing that the masses of stars that exploded was above 20 solar mass. And 1987A was a low mass progenitor because it was thought to be somewhere between 15 and 20 solar mass. And so we were, there was a problem with theory predicting that only stars below 25 solar masses would explode, and observations implying something different. There was a lot of uncertainties in analyzing those observations, and so theory went on ignoring the observations. But what happened in the end is more and more observations of supernova progenitors. Remember, for 1987A, we actually saw the progenitor. Well, we've now seen the progenitors for quite a few, and this is a compilation by Steve Smart in 2009 on the right, where he looked at the masses of the progenitors of supernova where we have observations. And in all but one case, the mass is below 20 solar masses, and the one case where it is above 20 solar masses, that's an upper limit, so it could still be within that, below 20 to 25 solar masses. And more data has come out since 2009, and they seem fairly consistent with this, which is most explosions occur below 20 to 25 solar masses, which you kind of expect with an IMF. If above 25 solar masses, you cannot, you have trouble driving explosions. And that's what the theory predicted. So I think now the theory and the observations are in line, and they were kind of showing that, this was a kind of a true prediction of the theory. So in 1999, when we made these predictions, the observers would come up and tell me I was wrong, right? So the change happened over 10 years to show that this is a true theory prediction that showed that our models may be right. Another way to constrain the models, and this is something that is more for the future, is general relativity and gravitational waves. The convection that we see in the engine produces distinct gravitational waves, and we can observe those and use those gravitational waves to constrain the convection in our model and prove that convection is true. And this is something that really gravitational waves will produce a very strong constraint on this convection, but it requires a nearby supernova. It requires a galactic supernova with advanced LIGO. The hope is that with next generation telescopes, we can move out a little bit further, and that will be allow us to have a better chance of getting some nice gravitational wave signals to constrain our models. The gravitational waves provide a really nice constraint of the engine for supernova. But this is not the only way gravitational waves constrain supernova. They also constrain it by looking at the mass distribution of these compact remnants. And I think Pablo will talk about how well gravitational waves are doing at constraining the masses of compact remnants. And I can't stress enough how important it will be to get the masses from both neutron stars and black holes from, not just observations of the masses, but the distribution of masses from gravitational waves. And I think that's something that's going to be an exciting field for the next, not just few years, but next couple decades as they get more and more precision measurements. But already the masses that advanced LIGO has gotten has started to shape our theoretical models, has started to tell us something about the convective engine. One thing that you have to be aware of is that LIGO has some, there's observational biases in every time you do observations, and LIGO is going to detect more massive black holes than it will the lower mass black holes, simply because it's more sensitive to them. And so you have to correct for that when you create a mass distribution that you give theorists. And the LIGO team does this. It's been doing it for over a decade. They even before they had observations, they knew how to correct for it. I'm showing a paper by Chris Boltinski in 2012 with Dan Holtz, where they actually looked at what would LIGO detect and what would advanced LIGO detect, and how does that compare to the actual mass distribution? So you have to worry about the biases, but we know how to correct for them, and those mass distributions are really telling us something about the supernova explosion. The kind of last observation evidence that I think I would like to talk about before going into some studies of the progenitors is the nucleosynthetic yields. In the engine of these supernova, we are now predicting a range of electron fractions for the ejecta mass. I have a plot here on the right by Adam Burrows et al., where he's studying he's doing these detailed neutrino transport models, and he's getting different electron fractions. And by studying the nucleosynthetic yields, we can actually constrain those electron fractions. And it not only teaches us something about the convective engine, I think in the end, it's going to teach us some neutrino physics, some nuclear and neutrino physics. It also, if you look at the detailed yields in this bottom plot or set of images from Sydney Andrews, where she's looking at changing the explosion energy of I think this is I didn't write the star down. I think this is a 20 solar mass star, but she's looking at the yields of scandium-47 as a function of playing with the explosion energy and looking at where it's produced. And it's produced not just, some of these radioactive isotopes are not just produced in the core, but they're produced throughout the star. And we can use the production of these radioactive isotopes to actually constrain both the explosion energy and the progenitor structure. I see that I'm running a little bit low on time, so I want to go quickly through this. One of the other things that we're looking at is how do the yields change if you have asymmetric explosions? Because we saw that we do have asymmetric explosions, and so there's a lot of studies of the yields through asymmetric explosions. This is work done by Greg Vance, where he looked at how the outflows move. And the kind of simple models we did a decade ago, or some people are still doing, are probably not enough to really study the yields. And I think we're going to be doing better and better models to study the detailed yields and compare them to observations. In the last few minutes, I wanted to talk about one other probe that we have for supernova that people are proposing, which is to look at the emergence, the early time emergence of X-rays and UV from supernova when the shock just breaks out of the star. So we have asymmetries in the explosion, we have asymmetries in the star, we have asymmetries in the circumstellar media, and all of those produce shocks that will appear when the shock just breaks out of the star and starts moving through the circumstellar medium. And there's a couple satellites that are being proposed that should be launched soon. Ultrasat is one of them. There's a bigger mission called CyBax being proposed that will observe the shock interactions of these asymmetry, as the shock goes through this asymmetric matter to try to constrain, what's really the asymmetries in these stars. And what I really like about this kind of study is it ties together laboratory experiments. So there's laboratory experiments trying to study shock progress through stochastic media. So on this left panel is a simulation of an experiment being designed at Los Alamos National Lab to study shocks through a stochastic media. And the size scale from this is actually at the level of 0.1 centimeters. So I have something that's a simulation of something that's at the size scale 0.1 centimeter. It's being run at the Omega facility in Rochester, where they use lasers to drive a strong shock through something. But the upper right middle panel is the same kind of shocks running through the circumstellar medium, where we have asymmetries, a kind of stochastic medium in the circumstellar medium, shock progressing through it. And it's the same physics. So we're actually calibrating and understanding that physics on laboratory experiments, and then we can apply it to supernova to go all the way to building an X-ray telescope. And I guess with that, I will end the talk. The point of my talk was to say, look, asymmetries, the asymmetries we observed in 1987A kind of gave us a really, drove us to the model that we now believe behind core collapse supernova. And since that time, since 1987, we both have developed the models that explain what happened with 1987A, but now allow us to do comparisons to other data and make predictions, things like what's the, looking at supernova remnants and the titanium-44 distribution, things like the remnant masses, and we're planning observations for things like gamma rays. So there's a whole set of gamma ray telescopes being proposed to try to study the nucleosynthesis better. Gravitational waves are going to bring a lot more observations to constrain this model, as we get both from the potential to see gravitational waves and neutrinos from a nearby object, all the way to looking at the compact remnants, which I think will really place the distribution of compact remnant masses and spins will really place some nice constraints on the engine. And finally, this last thing that I spoke about, which is shock emergence. This early shock emergence is another way to probe the asymmetries in stars. And with that, I'll end my talk. And thank you for your time.
We have a problem because Lorimer did not show up, and therefore we have no chairman at the moment. And the only thing we can do is to see if there are questions and remark. Can you see from, Gregory, can you see if there are questions from the...
Yes, please.
Yeah, so
you can answer directly.
Yes?
Yes, may I?
Jorge, just.
May I? Oh, okay. Hi, Chris. Thank you for the nice talk. Let me go back to the result of SMART. As you mentioned, so the range of masses that are the masses of the pre-supernova masses, right? But these numbers come from the archives, if I understand correctly, from archival data. But you can also derive those masses from the supernova model of the, I mean, from modeling the light curves. So when you model the light curves, these two masses coincide. So in passing,
So
you are.
Yeah, Jorge, this is a great question. So this is why when we initially predicted that the masses had to be low, so the theory models were saying that the engine modelers said that the masses had to be low, but the light curve modelers were saying the masses had to be high. And so the problem with modeling supernova light curves, and we've gotten better since the late 90s and early thousands, the problem was that if you don't get the opacities exactly right, if any kind of uncertainties in the models, and you can fit, you can get the wrong fit. And so we're getting better and better, trying to be more careful with our models. But light curve modeling is very difficult. So it's harder to infer the mass in the ejecta from the light curve models than it is by just looking at these HST archives and getting the progenitors. So they don't always agree, and it's partially telling us we have to work harder on our models. And I'll give an example. My team, we had gotten a very interesting supernova, and we thought we could only fit it with a parent stable supernova. And we were convinced we'd seen a parent stable supernova, and we fit the model. We could fit the data. And then Dan Kaysen came up with a fit where it was a lower mass progenitor, but he just had some shell interactions. And so he's able to explain the same data with a model that was, 1/10 the mass that we were claiming we needed, or maybe 1/5 the mass that we claimed we needed. And all it was is he put in some circumstellar media that the supernova shock was hitting, and that made all the difference. And in the end, I think Dan's model was probably the better model, and it was just, we found a fit. We said we were good, and we didn't think, oh, what happens if I play with the circumstellar media? So things like opacity, circumstellar media effects can really make it hard sometimes to infer a mass from the light curves. And so it's a hard job. So they don't always get the same answer, but I will say that the masses from this archival data, looking at the progenitors, is usually the more reliable one.
This is what I thought. Thank you for the detailed answer.
I see there's a question on the Q&A. Should I read it out?
I have a question. I'm Valerio Bozza, and my question is about the relations between the asymmetry in the explosion and the rotational and magnetic properties of the progenitors. Is it possible to find any correlations between the observed asymmetries, what we know about asymmetries in supernovae, and the distributions of rotational periods or magnetic fields of massive stars? It would be interesting to find the correlations between these things in order to understand the origin of the asymmetries.
Yeah, and one of the games that we've tried to do for that is you look at the kicks in supernova, and you ask the question. You can see in some of these, you can see the kick, and you can look at the rotation of the pulsar. So you have a pulsar with some kick, and you can ask the question, how is that rotation and the kick, are they aligned? What are you seeing there? And the evidence is not as ideal as, so there's some that look like they're well aligned, and so the kick is aligned with the rotation axis. So you can imagine if you have strong rotation, even without magnetic fields, if you have strong rotation, that's gonna limit the convection to the rotation axis, and you'll get a stronger explosion just along that axis. If you add magnetic fields to that, and I think, the importance of magnetic fields, I think there's a subset of supernova where magnetic fields are playing a driving role in the explosion, but I think for a lot of supernova, it's not. So I don't think magnetic fields were that important in, say, Cassiopeia A remnant. The data doesn't match that. But I think you could have magnetic fields be important. But the alignment between kicks and which you think is the direction of the explosion and rotation doesn't seem to be always true. It's true in several cases, but it's not always true. You would have to do. I think the jury is still out on that. I mean, I think we need more data to see how many supernova are well aligned with that rotation axis versus not. And we need more data.
Jan Novak, please, a short answer and a short question, short answer, please.
Yes, well, okay. Yes and no. People have included approximations for this. Jorge asked the question, are you including neutrino flavor conversion oscillation in the calculations? The answer is yes and no. People have put it in some of their models as a kind of but in a toy way. So we're not doing detailed neutrino flavor conversion calculations, but we have things where we change the heating to see how it affects it. And that can be an important effect. It's just really hard to include it in a first principles way. So there's a lot of work to do. There's been a lot of studies where you look at a simple profile and ask how important can neutrino flavor oscillations be. And there's also been some people that have instead just put in a toy. If they have that kind of importance, I'll add this extra energy deposition. But that's about the level that it's been added.
And Novak asks a question. Please formulate the question.
There is apparently audio problem, so we can maybe go on with the next speaker.
Okay. Chris, we will have to continue this discussion in the next days.
I look forward to it.
Okay, so we can ask our next speaker, who is Pablo Laguna, to share his screen.
Can you see it?
Oh, yes, we can see. The stage is yours,
Okay.
please.
How about now?
Yes, we can see it.
Okay, all right. Well, first of all, I want to thank Remo and the organizing committee for the invitation. And I'm delighted to spend the next 30 minutes telling you about numerical relativity, a little bit about where we are with the simulations, and also the role that those simulations have played in the interpretation of gravitational wave observations. I'm at the University of Texas, and we just recently established this Center for Gravitational Physics, and we hope to organize an in-person conference this coming year, and you will hear the announcement. All right, let me just start with kind of the flashy way to present the numerical relativity simulations. What you have here is in the upper left, it's a simulations of a binary black hole. This is as close as you can get, given the parameters that were published, to the event in 1905-21. In the upper right is the first detection of a double neutron star merger. And at the bottom is the one that we just heard from the collaboration last week. That is the two events that involve the merger of a black hole and a neutron star. So I'll just play the simulations. These are simulations done by our group. And what you see at the bottom, and the two of them is the gravitational wave produced by the event. And in the one with the double neutron star, you have two panels. In the left, you have the density profiles, and then the right-hand side, you have just contour plots of the gravitational waves. This is great. I mean, this is a way that one uses to mostly advertise or do press releases. But let's move on to how these simulations are actually used in connection with data analysis. This is the figure number 1 that is quite famous by now of the first detection of gravitational waves. And if you look at the second from the top row, you see the word numerical relativity there. You see it there in that the red line on the left superimposed with with reconstructed signal, and in blue on the right. So it is clear that there is some input, there is some guidance that these numerical relativity simulations have played in determining the characteristics of the binary. And that is what I want to spend most of the time. So next is, let me just start by giving you a sense of what is the different components in this. I'm going to concentrate for the moment in binary black holes, but also, of course, it applies to some extent with double neutron star and the mixed binary. So what you have here is that there are basically 3 stages. There is the early spiral, in which here you cannot, you can perhaps use post-Newtonian methods to some extent, but in the span that in this figure is mostly numerical relativity. That is, you have about 10 or 8 orbits before merger, and that is the typical span, and maybe a little bit more. I'm being too pessimistic. Is between 10 or 20 cycles that most of the numerical relativities can cover without being too expensive. The simulations continue to be very expensive, and I will spend the second half of my talk talking about what is the future of numerical relativity to address this. So you have about, in this figure, you had about, 8 cycles or so. At some point in the late spiral, that is when you see that the horizons have the largest deformation. Eventually, just about few m before you reach peak magnitude, that is when the merger occurs. And in this case, for the binary black holes, we call it the merger, when the first time that you detect the appearance of an apparent horizon that encapsulates the original 2 apparent horizons. And the end, you have the ring down. In my opinion, the next big frontier, so to speak, that we're going to see in this area will be precisely in the ring down. I mean, the detectors are going to be very sensitive to the point in which the signal to noise ratio in this part is going to allow us to investigate in exquisite detail what happens during the ring down. And even that you can treat this with perturbation theory, but in order to get the whole history of the whole history of the process, we need numerical relativity simulations that are capable to be accurate enough to assist in the data analysis of that. So this is in terms of how a binary black hole, the anatomy of a binary black hole, but let's just put it in context of what numerical relativity covers. And this picture has been, it's become more like a requirement in every of these talks, just to put in context where numerical relativity plays a big role. So in this plot, having the horizontal direction, the mass ratio of the binary, and in the vertical direction, a measure of the compactness, okay? So numerical relativity, right now, the parameter space that we're able to cover is at this range, in which you have mass ratios of, comfortably, you can probably go to 1 to 20, 1 to 40. There have been heroic runs that go to 100, but I think in terms of production that assists data analysis, it's safe to say that is 1 to 20 and so on. And the same thing goes with compactness. Now, you have the other 2 approaches, the one that is the gravitational self-force, in which you have a test particle, so to speak, in the presence of a massive black hole. And you can do that with perturbative methods. The other end of the spectrum is in which you have the 2 objects that are separated enough and moving at speeds not comparable to the speed of light, in which you can apply post-Newtonian theory. So notice here that there is a gap. This is not very precise, but there's still room here to be able to numerical relativity to go get closer or gain more real estate in that direction. All right, so today, numerical relativity can do the following. This is just in one slide, trying to give you a sense of where we are. Notice that this is more than 15 years since the first time that two black holes were collided, and that was by Franz Pretorius using the generalized harmonic formulation. And the following year, two independent groups, one that was at that point in University of Texas at Brownsville, and the other one at Goddard Space Flight Center, they were able to do another collision using a different type of formulation. In this case was the BSSM formulation, and introduce what is called the moving punctures method. That is a combination of how you apply the gauge conditions or the coordinate conditions. But these days we have several codes. This is I have another slide with a more comprehensive list of that. I'm just listing here a few. There is the Einstein toolkit. This is our code that is based on the Einstein toolkit. It just has some minor differences. The group on RIT has another one, a spec, that is used based in generalized harmonic coordinates. So there are many codes. Again, there are also different formulations, BCSSN, Z4, generalized, and different gauges associated with it. The typical approaches is, in one case, you go and excise the singularity. That is, you remove from the computational domain a region in which you believe the black hole singularity is present. The other one is the puncture approach. And that one, it's a little bit, from the computational view, in my opinion, it's not as challenging. You don't have to do anything with the computational domain. The gauge takes care of things by itself. Now, in terms of the data analysis, or in terms of how numerical relativity is helping the effort in analyzing data collected by interferometers, is by building catalogs. And those catalogs are used typically for two types of efforts. One of them, the waveforms in the catalogs, are used to calibrate these models of templates. And there are typically two main ones. There are phenomenological templates, and there is a EOV templates. And most recently, we had these surrogate models that they use these things. So those catalogs are very helpful in that, and we hope that the more and more people doing numerical relativity will help in building these catalogs. Most of them are for binary black holes, but pretty soon we're going to be having for the neutron stars in binary systems. And again, there is also interest that these codes are used beyond GR calculations. Some of them have been used to alternative theories of gravity. So here is a very quickly a list of the codes that is more comprehensive. Some of them are open source. Some of them directly contribute to waveform catalogs. Here are the formulations that I was mentioning here. They basically are BSSN or BSSN-like type of formulations and the generalized harmonic conditions. And some of them include hydro. And as I say, there is now an effort to go beyond numerical relativity. So one thing that it is important, given the different codes, the different formulations and so on, is to do comparisons. That will help us to add confidence that the predictions that we make are robust. Before the first detection, there were attempts of just doing comparisons. There were studies doing comparisons, direct comparison among the groups. There was the first one, the NINJA, the NRAR, and so on. And after that, there were comparisons that were doing mostly to compare numerical relativity with gravitational waves to do parameter estimation and so on. Now, the challenge with this is there are several aspects that are very challenging. Some of them, for instance, still is not clear if we have a good definition of eccentricity. Comparing simulations involving precessing spin is very difficult, even just at the point of starting deciding about initial data with all these different codes, different gauges, and so on. Joint radiation, that is that very spurious radiation that you get because the initial data is imperfect, that could be a problem, especially for highly spinning black holes. And as I mentioned, one of the things, given the different flavors of codes and so on, it also, we had to pay attention about when we set these comparisons about the initial data. All right, so after the detections, then not only the numerical relativity simulations were used to be able to calibrate or to improve the waveform models, but they also were used targeted to specific events. And here is just not a comprehensive list, but I'm going to just put in some of them, in which numerical relativity play a key role in these follow-up studies after the event. In particular, the figure here on the bottom right is from the Haley et al. Paper, in which we did comparisons of basically 3 groups: the SXX, the one in RIT, and at that time we were at Georgia Tech. And the idea is to be able to see not only how well each of the numerical relativity simulations perform, but also in context with what a specific event. Okay. Now, the open challenges in this type of work is, can we just do it automatic? That is, can you have a trigger event and then just be able to do all the simulations that are needed? Okay. So for the future, okay, what we need is we're going to have future ground and space detectors that are more sensitive, and even LIGO, of course, that is a part of it. There is potential for very large SNR, signal-to-noise ratios, especially with LISA. So what we want to know is about the errors. I mean, how well a numerical relativity will perform on that. And let me just show you a result from a recent paper from our group. So this is making an estimate of what will happen. And if you have, for instance, here on the left here, that the LISA, you can see here that in the LISA and the Einstein telescope, the residuals are above the noise curve. So that means that if you want to subtract the signal, it could give you a false impression that there is a signal present there, and it's just a result of the numerical errors. Let me skip this because I'm running out of time. So here is from the simulation from, and that's why I think numerical relativity will be able to play a big role as more mixed binary events take place. This is a black hole neutron star merger. The mass ratio is 2. The black hole is two times the mass of the neutron star. And here are some snapshots of the merger. And contrary to what happened with the merger that were announced a week ago, here, the disruption of the neutron star happens earlier. So you're able to see that there is a hint of an accretion disk, so to speak. Now, that has the consequence that as the black hole relaxes, that is, as you get the ring down of the black hole, there is still matter around that is accreted. So here in the right-hand side, I have a plot of what, if we had a binary black hole, would be the ring down of the final black hole. Here, it's clear that you don't get that. And the main reason for that is because you still have matter accreted into the system. All right. So the challenges, as I said, that we have solved things for mass ratios of 15 or less. There are spins, moderate spins. We also have tens of orbits and so on. I think what we need to go is, first of all, we need to increase the accuracy of the simulations. We need to have more cycles. We need to have a better measure of what we mean by accuracy related with respect to data analysis. All right, in the last few minutes of the talk, I sent an email to my colleagues in the community, asked them if they wanted me to advertise or to give an update of their efforts for what is coming next in numerical relativity. So here are just few examples that I received. So this one is for David Nielsen and collaborator Eric Hirschman. I'm very excited about this project. This is one of the things that we have struggled with, at least with our current code in the Einstein toolkit, is adaptivity, adaptive measure finding. I think the approach that David and Eric and collaborators following is very promising. Here is just a snapshot of how that adaptivity will work. And this will be very, very helpful for binary system with large mass ratios. So in that gap of that plot that I was showing, I think it will able to get it closer to the cell-4 side of things. Here is another example. This is also that I think has great promise. This is by Zachary Etienne, and now at the University of Idaho. Is black holes at home. And here again, he paid very careful attention that activities are prominent. And what he had tackled that with is by doing a very clever way of combining spherical coordinates in multi-patches and so on. So he is able to get very efficient structure, even for mass ratios of 1 to 6 and so on. And the performance is great. Still, it's on the work. The plot here on the right are comparisons with the Einstein toolkit. But I think this is something that, in my opinion, once that he plans to do to be open source, the community will benefit tremendously. Bruno Giacomasso and collaborators sent me this. They are working with the Spritz code, that is a general relativistic MHD code with neutrinos. It is publicly available. This is based on the Einstein toolkit. And in order to handle the MHD, they do the vector formulation, and it supports several. This is going into the direction of adding more physics to the codes to be able to deliver that. And the next one, oh, this is the same group, but this is more detail about how to go from conservative variables to primary variables. All right, so there is another code that this was provided to me by Vernuzzi, and this is a GR Athena ++ code. And again, here working on the AMR side, so this is the third time that I repeat AMR. I think that is a big effort in numerical relativity that it will allow us to go to the next level. And they use the Z4 formulation. And again, performance is looking very promising. In this case, here's an example of a waveform compared with other methods. Luciano Resola, he has been working on this discontinuous Galerkin method to do the GR and MHD. Here on the left here are two, and the left is a snapshot of a test doing a blast wave. And in the right-hand side is a complementary work that uses is aimed at the relativistic lattice-Boltzmann equation. All right, and when I was talking about Zachary Etienne's work, I mean, you saw that is spherical type coordinates. I think the ones that started this, the first paper was by David Brown, but I think my friend Thomas Baumgart has been pushing this, and these are two examples that of calculations that he has done that now this approach of spherical polar coordinates are implemented in the big codes. One of them was in revisiting the Chopwick critical collapse, and in the right-hand side was about a neutron star inside of a small black hole. All right, so I think that gravitational waves and multidimensional astronomy are here. That's not nothing new. But what I want to emphasize, the future ground detectors and space detectors will, because of their sensitivity, because of the ability to detect signals at very high SNR, will make that numerical relativity will need to work harder on the one hand, but it will be able to provide means to predict and interpret gravitational waves. There is many work ahead to be done, and but I will stop there and take some questions. Thank you.
Well, Pablo, very beautiful talk and extremely interesting. But let me express some concern. You have shown this classic result of 1509-14, which was detected the first week of entering into function, still not yet operative, of the LIGO detectors. And the data, these data were superb quality. And it was possible to work on them. And in fact, with Rodriguez, we did precisely what you are planning to do, to look at the ringing modes, and we found some conceptual difficulties in the result of the ringing modes. And we published that, and I will send you the paper. But what worries me, that in the 6 years since, there has not been a single signal of clarity and possibility to work in such a detail since. Apart, of course, 1708, 17A, which needs a different problematic. There we don't look at the ringing modes that you are mentioning. Therefore, I feel just my concern. And this is my point. And also the difficulty we are encountering in 1708, 17 is very important. Therefore, yes, let's see if we go on and we find some good examples. 6 years is a long time compared to the first week of operation. And I leave just with that, with my concern.
Right. I mean, I share your concern, but I mean, I think it's, if I'm not mistaken, the main issue is how the SNR accumulates during the ring down. I mean, if the SNR is high enough, and it's my understanding that we have not seen an event in which we get yet the sensitivity from the detectors to have a clear ring down. At least even, I mean, the hope is that we see more than one mode and to be able to do more interesting things. But that is just a matter of time as the detectors improve. So
I will send to you and to everybody our paper of Rodriguez, because the result, as they publish, they are not consistent, in our opinion, with fundamental physics, like they were not consistent in fundamental physics, the result of Misner. But anyway, this is in the literature, and I will send to you. Thanks.
I think Chris has a question.
Yeah, there is a question from Chris, please.
Yes, Pablo, so this is where I'm starting to get really excited about gravitational waves, because it looks like the numerical simulations are getting higher and higher fidelity. And, you know, there's already been some studies on neutron stars looking at the neutron star equation of state. But I can envision that you can do even constraints on if there's strong magnetic fields in these neutron stars. Will that also affect if you have these merging neutron stars with strong magnetic fields? Will you be able to probe the magnetic field properties as well? And when I say will you be able to do it, I'm thinking in an era where we have next generation telescopes and a nearby event. Is this what some of the science we'll be able to do? Will the theory be able to be ready for it when these new detectors get out there?
I think so. I mean, in some of the examples that I gave there, is people are really I mean, I think they're working in two fronts, and some groups do it at the same time. One of them is more into the software engineers, so to speak, okay, and trying to improve the AMR, trying to improve efficiency of the codes and so on. The other one is into adding the physics or the microphysics or magnetic fields and so on. And I think that both avenues are making great progress. Now the question is, are we going to be, for instance, with regard to LISA, are we going to be ready when we start getting that there? I believe we will. Okay. And now in terms of the physics content, That one I don't know. I mean, that is, as you were just mentioning with your simulations, that it's, you know, it's a more painful process, I think, when you're starting to add all these very complex, you know, microphysics or multiphysics. But I think the future is looking good, in my opinion. I think we have another question.
Yeah, from Bing, please, Bing.
Thanks, Pablo, for the nice talk. Yeah, so my question is for neutron star mergers. So we now know that there are simulations up to forming the black hole, maybe through a hypermassive neutron star phase briefly. But from the, say, GRB observations, there seems to be evidence that after neutron star mergers, you might probably produce a much long-lived neutron star to a supramassive phase or even stable phase. And there must be also secular gravitational waves released during that period of time. So is there any efforts trying to simulate this phase? I know it's a long shot to observe the gravitational waves, but is it going on to simulate the gravitational waveforms?
I think that that is a great example of in which one can go and, you know, you work in the binary maybe with these coordinates that Zach Etienne is talking about, but at the end, if you can switch to these spherical like coordinates that I briefly mentioned that have been pioneered by Baumhart, I think then the codes can be more efficient because it's the geometry, it's more in tune with the physics that is happening there. I mean, I'm talking about the geometry or the coordinate system in there. And I think that then we'll be able to do a much longer simulations. The same thing, for instance, in another context, right now, the 3D numerical relativity simulations that, for instance, in some of the groups, including mine, we're doing for rapidly rotating neutron star. If you do it in Cartesian type coordinates, you're very limited, okay, and to do the long term. But with these coordinates that are tailored to what the problem looks like, I mean, in this case, more spherical looking, I think that is where we can extend the life of the simulations to be able to address maybe that regime that you're talking about.
But there certainly the merging of the two neutron stars is a field in which there is a clear signal of JEV radiation. And therefore, this will be the ideal case to tune to the detail of the JEV radiation, the models, and see if there is a coincidence with the gravitational wave. But definitely, that is a very promising direction to gain from the analysis done the details of the JEV radiation, which must be coming out of the binary neutron star merging. We have beautiful examples, 09, 05, 10, many, and 5 or 6 of them.
Thank you.
Probably we can move on with the program. If there are no more questions. The next speaker is Victoria Caspi, who just joined us. Please, Victoria, can you share your screen, please?
Yes. Can you hear me?
Yeah, we can hear you and we can see the slides. We can see you.
Okay, wonderful.
Please, you can hear us.
Okay, yeah, thank you very much. And I just want to thank the organizers for this. You know, the Marcel Gross mini meeting is always such a wonderful conference, and it still is, even under these less than ideal circumstances. I've been really enjoying it. So thank you to the organizers for all the hard work they've put in. And I'm here to tell you today about observations of fast radio bursts. So what are fast radio bursts? These are bursts of radio waves that last just a few milliseconds. They're highly dispersed. That is, they suffer cold plasma dispersion, as we see ubiquitously for galactic radio pulsars. You can see an example, the famous example of the very first discovered fast radio burst by Lorimer et al. Here You see time on the x-axis, where this is just a few hundred milliseconds, and on the y-axis is radio frequency. And you can see the horizontal line is just some terrestrial interference, but the signal is this sweep that comes through, which is the dispersed radio waves, which when de-dispersed produces the inset plot, where we see nothing but radiometer noise before the event, then the burst, and then nothing subsequently. We know that this phenomenon is ubiquitous. It's not something rare, in that the all sky rate, roughly speaking, is about 1,000 events across the whole sky every day. And they're approximately isotropically distributed, but all of these statements I'm going to make a little more precise later in the talk. The dispersion, the degree of dispersion, as I'm about to explain in more detail, is consistent with these objects coming certainly from well outside the Milky Way and cosmological distances, which of course implies very large energies. The range is quite wide for fast radio bursts, anywhere between 10 to the 35 and 10 to the 43 ergs for the population observed thus far. And for reviews, you can see a couple great reviews by Emily Petroff and collaborators, and Jim Cortez and Shami Chatterjee. So the dispersion, the fast radio burst source, we think, produces all radio waves here depicted with colors at the same time. So the burst happens, we think, at the source at the same time, and all of the dispersion is due to intervening plasma, the cold plasma. The free electrons basically disperse them so that the high frequencies arrive below the low, oh my goodness, so sorry about that. Below the high frequencies arrive before the low frequencies. And we can model this dispersion using a model for the galaxy, which, if you could view it, you're seeing it here from above. And here would be what the distribution in the galactic plane looks like of free electrons. You see spiral arms there, it's galactic center. And you can also plot it as a contour plot, as was done by Cortez and Lazio back in 2002, where the little Pac-Man here is Earth, and here's the galactic center. You see spiral arms. And these are contours of constant total column depth of free electrons, which we refer to as the dispersion measure. It's the integrated electron density along the line of sight. This model for the free electrons in the galaxy is a three-dimensional model. This is just a slice through it. But in any direction, if you observe some sort of transient radio burst, be it a pulse from a galactic pulsar or an FRB, from the dispersion measure, you can infer a distance. And in particular, the models for free electrons, they eventually run out of free electrons in the Milky Way galaxy. So for any direction on the sky, there is a maximum number of free electrons that we believe the Milky Way can have. And this is how we infer the extragalactic distances of fast radio bursts. Because for the Lorimer burst, from this, the slope of the parabolic trend in this dispersed plot, we know that the dispersion measure of this burst was about 375 in our DM units, whereas the maximum inferred from models of the galaxy is just 25. So there's way more free electrons than you can account for in the Milky Way galaxy. There's no foregrounds there. This was studied very carefully. There's no object in the front, like a dense H2 region in the direction of the source. Basically, it implies that this source had to be way outside the galaxy and must be extremely bright, therefore. Now, when we say cosmological distance, how do we infer that? Typical models of the IGM, which will soon be refined by fast radio bursts, suggest, of course, there should be a very ionized component in the intergalactic medium, and that the dispersion measure in the IGM should be, roughly speaking, 1,200 times the redshift. That's very rough, of course. But if you apply that to that Lorimer burst, you get a redshift of 0.3 or a distance of a gigaparsec. So that's why we infer cosmological distances. But we know, of course, that's likely just an upper limit, because FRB must come from some host galaxy, which itself has some interstellar medium and some DM component. So the total DM, which is the only thing we can measure, is equal to the DM from the Milky Way's ISM, interstellar medium, perhaps some halo in the Milky Way. Perhaps galaxies have halos of free electrons. We think they do. The IgM component and any host component. And so let's say you were to split, we know the Milky Way components. We have good estimates of them anyway. If you subtract that off the Lorimer burst dispersion measure and then divide it equally between the IgM and the host, okay, so that's still 500 megaparsecs, roughly speaking. So it's still a lot of energy in these bursts. So basically, what have models been suggested? I'm going to say this very briefly because the talk after mine is by Bing Zhang, where he's going to delve into models in much more detail. But just to set the stage, first of all, for several years, there were more models than there were events. That's certainly no longer true, as I'll describe. But in any case, we know from just the brevity, the few millisecond durations of FRBs, that the source size from light travel time arguments has to be, very compact. So we're talking about some sort of compact object. Neutron star comes to mind. But the energy here, the energies involved, I mentioned, they're very large, but they're not revolutionary types of energies. Gamma ray bursts have isotropic energies 10 to the 53, or many orders of magnitude greater than those in FRBs. On the other hand, we know from the brightness temperatures of these objects, they have silly, enormously high brightness temperatures, similar to we've observed in radio pulsar. So something about the radio emission mechanism, it has to be coherent. That suggests strong magnetic fields, perhaps. Now, in terms just from energetics, there's easily enough energy in cataclysmic events, and for a long time, that's people thought that all FRBs might be related to cataclysmic events, perhaps supernovae. But there was always a problem. The opacities in supernovae at the start are quite high. It might be difficult to get radio waves out of there. And for compact object mergers, like we've just been hearing about, the rate, it's not 1,000 per sky per day. And that 1,000 per sky per day is just above some flex threshold that's, for current technology. The rate seems off. Then one looks to isolated neutron stars. We know the Crab pulsar, we've known for years, has giant radio pulses that are quite luminous, but still nowhere near as luminous as FRBs. They're orders of magnitude, both in energy and luminosity, too low. Another option that's been discussed a lot, and I believe is currently the favored model, at least for some FRBs, are magnetars, that is extremely highly magnetized neutron stars, the highest magnetic field objects we know of in the universe. There's certainly enough magnetic energy in those objects to somehow power FRBs. Exactly how that happens is something Bing Zhang is going to try and help you with later. So there is a great FRB theory wiki that you're welcome to look at. And also I suggest you stick around for Bing Zhang's talk if you want to know more about models. Now, one hugely constraining observation of FRBs is that some of them repeat. So Lorimer burst, we've never seen again. But this particular source, FRB 121102, discovered with the Arecibo telescope that, of course, is no longer around with us. This was the first FRB found to repeat. And here you can see de-dispersed repeat bursts from the same position on the sky at the same dispersion measure. And this immediately, with a single observation, ruled out cataclysmic models, at least for this source. There were 10 of these bursts in an hour after several months before the first burst. And since that time, there's been all sorts of beautiful observations, including by the FAST telescope. Over 1,000 bursts from this source have been seen since its discovery. And you can see the bursts come in all sorts of interesting different brightnesses. You see a really bright one here, different spectra. The spectrum here, these are now the radio frequency always on the y-axis and time on the x-axis. You see the spectrum's rising to lower frequency. Here, the spectrum's rising to higher frequency. A whole variety of morphologies, which itself is curious. But one of the most interesting questions it raises is, do they all repeat? So most FRBs we have not seen to repeat, but perhaps we just haven't waited long enough. Now, FRB, in terms of burst morphologies, most FRBs show single peaked pulses, a single pulse that is broadband, in fact, like the one that I'm showing you in this inset here, although this one has an interesting feature that it is scatter broadened, that is from multipath scattering in the inhomogeneous interstellar medium or intergalactic medium. We don't really know where the scattering comes from for FRBs. You can see the telltale scattering tail that lengthens at lower radio frequencies with a characteristic frequency to the -4th power for that exponential tail duration. So some of them show scattering. Some of them show multi-peaked and complex morphology. So here's a montage. These are actually FRB 121102 events where you can see all sorts of interesting multi-peak structures. This is postage stamps. Each one of these is a different burst. Again, all de-dispersed, frequency versus time. And you can see this interesting downward drifting frequency structure in some of these bursts. We call that the sad trombone effect because it sort of goes wah, wah, wah. We don't know what it's caused by, but it is seen commonly, particularly among repeating FRBs. Now, you might ask the question, okay, where are these coming from? You want to infer cosmological distances, you should know, why don't you just go and see what galaxy these events are arriving from? And we, of course, love to identify host galaxies for all fast radio bursts, because that would determine their redshift and set the energy scale very unambiguously, and also answer the question, what kind of galaxies are these coming from? Are these young objects? Are they in star formation regions? Are they old objects? But the problem is that, the Lorimer burst was found with a 64-meter Parkes dish, which has 30, typically somewhere between 15 arc minutes, 30 arc minutes, depending on observing frequency, field of view. And so there's thousands of galaxies that it could come from. And even if you go to Arecibo, which of course has a larger or had a larger diameter, the field of view is smaller, but that's still not good enough. You really need so there's typically many galaxies in single dish radio telescope error regions. You really need an interferometer like the Very Large Array or VLBA to identify host galaxies. Problem is, the sorts of telescopes that are good at discovering FRBs have wide fields of view, or relatively wide fields of view, but they can't localize well. The sorts of telescopes that can localize well can't find FRBs because their fields of view are too small. On the other hand, if you have a repeater like 121102, you know where to look. And as long as you're patient, the interferometer can localize it. And this is what was done using the Very Large Array. The very first repeater, 121102, was localized to within the circles. Here are the Arecibo uncertainty regions, and that dot is actually the counterpart as was identified with the VLA. And it was then observed optically with the Gemini telescope once we knew the precise localization. And we were quite surprised to find that that repeater is in a dwarf galaxy at redshift 0.2. So the cosmological distance was confirmed, but I think everyone was surprised that it was in this dwarf galaxy, and subsequent observations using the European VLBI network and the VLBA showed that our FRB is in a star formation knot. There's also Hubble Space Telescope observations that showed this, which suggests that this repeater is young if it's associated with a star formation knot inside that tiny dwarf galaxy. It was also coincident with a continuum radio source. You can see this is the radio continuum observations are here. You see it's variable. The red points are where we saw bursts. So the variability of the radio source seems to have nothing to do with the bursts as far as we can tell so far. It's curious. It's an observational fact. We don't yet know what that radio continuum source could be related to the star formation. But since that time, there's been 6 more, or at least actually today, as of today, there's 14 more localized. I have a montage here of 6 more localized fast radio bursts, none of which are repeaters because the Australian telescope SKA Pathfinder or ASCAP, which is an array of telescopes in the outback in Australia, it is capable of finding FRBs and of localizing them to arc-second precision at the same time. And so today it has localized some 14 FRBs, and none of them is in a dwarf galaxy. As far as we know, all of them are associated with massive galaxies. And indeed, here's one associated with a beautiful spiral galaxy. The story here is still developing. There's quite a diversity in the host galaxy properties. There's certainly all, so far they're all at redshifts of, you see the redshifts here, 0.5, 0.4 in that region. Sometimes you find FRBs that are in the outskirts of the galaxies, and that's quite interesting. Oftentimes you find them in the spiral arms or in the near the centers of the galaxies. The fact that you can't, so the question of the environments of FRBs is quite interesting. The types of galaxies they inhabit is quite interesting. But on top of all that, when you have the redshifts to the galaxies, you can then do interesting studies that are relevant for cosmology, like for the missing baryon problem, for example. With just 5 localizations, or 5, as they called them, gold-plated localizations, which they felt they could include in their statistical sample, Macquart et al. Could plot redshift on the x-axis and cosmic DM on the y-axis. And what they mean there is extragalactic DM. So they've subtracted off the host contribution, they've subtracted off the Milky Way contribution and also an estimate for the host contribution. That's a problem. You don't know what the host contribution is, but you can take an average estimate, which is what they did. And what they show is that this is the Planck cosmology prediction for what you should see here. And the gray region is estimated scatter because of large scale structure. But in any case, what they find is that the FRBs localized with the ASCAP telescope all fall in the expected range, which suggests they have identified the missing cosmic baryons. I think the story here is still developing because there's estimates and assumptions that have gone into this that I think still need to be checked. But it certainly highlights the importance and the potential of fast radio bursts as novel probes of large-scale structure and more. So in the literature, it's fascinating. We had a wonderful talk by Amanda Weltman, who described a lot of these potential applications of fast radio bursts as cosmic probes. And the reason they're so interesting is because they have this dispersion measure and because you can measure this scattering history of the burst since its emission. And I haven't had time, but you can also measure scintillation. And you can also measure rotation measure when you have polarimetric observations of FRBs. There's so much that gets imprinted on an FRB burst that can teach you about the path, but both some combination of the environment, the local environment, and the path to us. So you can study the missing baryons and the distribution of those baryons, whether they're throughout the IGM or concentrated in circumgalactic media and halos. You could study galaxy clusters. If you can find very distant high redshift FRBs, you could in principle study the epoch of reionization. Through polarimetric measurements, the IGM and magnetic fields. You could do gravitational lensing experiments and perhaps constrain nature's dark matter. You can in principle measure cosmological parameters. There's so much you could do. But for all of this, you need more FRBs. So a handful is really not going to do it for you. You want to determine their nature. You want to know if they all repeat. You want to realize their potential as cosmic probes. And for this, really, to do this kind of project, you need a radio telescope that has a very wide field of view and high sensitivity. And so that brings me to the CHIME telescope, which is, CHIME stands for the Canadian Hydrogen Intensity Mapping Experiment, which is located in Penticton, British Columbia, at the Dominion Radio Astrophysical Observatory. It's in this lovely valley, which shields us from radio frequency interference. Well, I mean, it doesn't totally shield us, but it gets a lot of it out. CHIME is an unusual radio telescope in that it consists of cylindrical reflectors. There's 4 of them. They're each 20 meters by 100 meters. So as we like to say in Canada, then units, the collecting area is about 5 hockey arenas. The cylinders are oriented north-south, and this is a transit telescope. There's no moving parts. So the sky drifts overhead, and we observe the entire sky, the entire northern sky every day, 24/7. Along the axis of each telescope are 256 dual polarization feeds that are sensitive in the frequency range 400 to 800 megahertz. And the geometry of the telescope, in that it focuses in only one dimension, allows us to have a very high field of view. So in the north-south direction, our field of view is about 120 degrees. In the east-west direction, it's about half a degree, depending on radio frequency. So we're talking about 220, roughly speaking, depending on how you calculate it, about 200 square degrees. And that is very good for detecting transients. Of course, the telescope was designed for a cosmological experiment to study redshifted hydrogen gas, but it also turns out to be a fantastic transient detector. Very quickly, this is the CHIME FRB team standing in front of it, so you see the scale of this project. And this is really run by many students and postdocs. Prior to CHIME's turning on, this was the histogram of the number of FRB detections by the different experiments. And now that CHIME is turned on, we're finding hundreds of fast radio bursts, which is very helpful for the field. And one of the first things that we did, because we see the sky every day, over and over again, it's very easy for us, compared to other telescopes, to identify repeating FRBs. And so we've published our first 18 repeaters. So prior to this, there was only the 121102, the Arecibo repeater known. And you can see a sort of a montage of some of our repeater bursts. And when you have many repeaters and you have many FRBs, you can start to do interesting statistical comparisons between repeaters and non-repeaters. And so one of the first things we noticed is that repeater bursts tend to be broader, that the durations of repeater bursts, and you can see here in this plot, this was at the very start when we only had 12 non-repeaters. Since then, we have hundreds, and I'll show you better plots of this in a second. You see the non-repeaters are all very narrow. They fall in this first bin, whereas the repeaters are quite broad. They extend in much wider in pulse width. So it's interesting, suggestive, possibly different emission mechanisms. We started finding strange things in our repeaters as well. We were very surprised to find a 16-day periodicity in one of our repeaters. You can see here in the plot, this is the periodogram, and you see the spike where we don't see that any of those kind of features in any other sources. And here you can see the CHIME exposure now. This is now date on the x-axis, and the CHIME exposure is in black. We have plenty of exposure outside of the gray activity regions that occur every 16 days. And all the red triangles are where we see bursts. So it's very clear this source has activity every 16 days. It's a 4-day, roughly speaking, 4-day activity window. And you say, okay, what could cause that? 16 days, could that be an orbit? Is this object in orbit around another star? Is that a rotation period, or is that a precession period? And Bing Zhang's talk, I think, probably will address that. I think one new result that just recently came out of the aperitif LOFAR telescopes, also combining with CHIME data on the right, you can see that the lowest frequency, the LOFAR observations, are seen in this plot too, tend to come later in that activity phase, in that activity window. So that there's a frequency dependent activity window, which is quite curious. We heard some interesting ideas for what could cause that in the FRB session that occurred Monday and Thursday of this week. Another big surprise that we had with CHIME FRB was the detection of a very luminous radio burst from a Milky Way magnetar. I see, how much time do I have left? Have I run out of time? Uh-oh, are you all gone?
It's so exciting that we we are still following. I think you still have 5 minutes.
5 minutes. Okay, that should be fine, especially if I talk really quickly, but I'll try not to do that. CHIME discovered, and as well, a Caltech experiment, Bochanek et al. Saw simultaneously these radio bursts from a galactic magnetar, extremely bright. This lit up the CHIME telescope. And that brings us to this plot on the right, which shows distance in parsecs on the x-axis and observed fluence on the y-axis. The galactic radio pulsars are here, and FRBs are over here. You see very far in distance. And you know, the previously we've seen some radio emission from magnetars, but it's all been relatively faint. In fact, the brightest one is over here, so quite a bit brighter than even the Crab giant pulses, which line up, which appear on this line. But the CHIME FRB source, the SGR with the huge bright luminous event that happened last April, is way up here. It's much, much brighter than any galactic radio, neutron star we've ever seen. And these lines now, these diagonal lines are lines of constant energy. And you can see that the energetics involved in this magnetar burst are starting to be comparable to those of the lowest energy FRBs. So they line up, and if this source had happened in a nearby galaxy, it would have looked just like an FRB. On the other hand, there's plenty of FRBs that are many orders of magnitude. This is 3 orders of magnitude per line, over 6 orders of magnitude more energy than is seen here. So it suggests that some FRBs could be magnetars, but I'm not sure all FRBs are necessarily magnetars. Recently, we also found a very nearby FRB located in the outskirts of M81, the M81 spiral galaxy. It looks like it's far in the outskirts, but this is an H1 map over here, where you can see, in fact, it's well within the H1 disk of M81, which is at 3.6 megaparsecs. So this is the closest known FRB, and it makes it a great target for prompt and other follow-up observations with X-ray telescopes, and that is currently underway. And very new, very recently, thanks to European VLBI network observations and detection of the source, it's been localized to a globular cluster in the M81 system, which is very curious because globular clusters have old stellar populations, and magnetars are very young objects as far as we know. Now, could you form a magnetar from, say, merging neutron stars? I don't know, perhaps, but it's very curious. And very finally, in the last few minutes, I want to mention we've just put out our first catalog of 535 fast radio bursts from CHIME FRB. That's from 492 different sources. Some of the observations we've been able to do with this treasure trove of data, we now have a very nice log n, log s relation with a power law index for the cumulative fluence distribution of -1.4 plus or minus 0.11, which is consistent with a non-evolving population in Euclidean space. And you say, wait, they're cosmological, but realize the CHIME FRB population, I'll show you shortly the DM distribution, it peaks around 500, which is at a redshift 0.5. So it's not surprising. We think as we detect more events, and we've already, in our paper, we show there's a hint already of deviation from simple Euclidean space. We've measured a very precise sky rates, and we have an evidence for very large population of highly scattered undetected events in our band. Oh, is my time running out? If my time is running out very quickly, I'll just say that we've looked at all sorts of interesting distributions of properties, comparing repeaters with non-repeaters. We've bias corrected our sample very carefully. We've done a very careful distribution on the sky analysis. This is Alex Josephi's work, completely isotropic, no coincidence, no dependence on galactic latitude. Burst morphologies, both comparing repeaters and non-repeaters, the morphologies and spectra are very, very different, suggesting different source classes, perhaps. We've detected a correlation with large-scale structure in the redshift range 0.3 to 0.5, which suggests a large fraction of FRBs are in dark matter halos as the survey galaxies. I'll skip that one and just summarize. There's a lot of observational phenomenology. It's still developing. We're measuring now distributions of properties in addition to individual source properties now. I think this is all going to come together in the next few years, and we'll be able to address the major open questions, which I list here, but for time, I'll just keep them up there. Thank you.
Thank you very much. We have we missed the chairperson, therefore I take this duty. Let's see if there are questions, or otherwise we proceed to the next lecture.
There is a question in the discussion,
Yes.
question answer. Please
Okay.
have Jenny Wagner. Maybe she can
Jenny Wagner.
directly ask the question, please.
Are repeating FRB coming from gas-rich regions in host galaxies?
Yes, can you hear me? I was just wondering whether the said trombone effect might be caused by some delay due to gas scintillation, scatter broadening, something like this.
Yeah, so there were two questions asked, so I'll answer the second one first. So there are plasma lensing models for FRBs. It could be some sort of propagation effect. However, generally speaking, in those models, they don't predict only the downward drifting. You might also see upward drifting. So we don't really know what the source of the sad trombone effect is, but at least in the propagation models we've seen, there isn't a reason to prefer a certain direction. And then to the first question that Remo asked about whether they come from gas-rich regions, well, I just mentioned we just localized one repeater to a globular cluster. So some of them, yes, seem to be in fairly gas, so FRB 121102 is in a star formation region, it's rich with gas, but the second repeater, the periodic repeater, sits just outside of star formation region. So there's not that many repeaters localized, and the story is still diverse.
Okay, thank you
Thank you very much.
Let's proceed with Bingzang then. Bingzang, are you there? Are you ready to go?
Yes, sure. Let me share my screen.
Okay.
Okay, hold on. Sorry for that. Let me go check something. Okay, thank you, Remo and all organizers for the hard work and for the invitation. And it's my pleasure to talk about the physical mechanisms of fast radio bursts following the nice review of Vicky. So I will start with this figure. This shows the number of publications actually made by Di Li. Number of publications in the GRB field as compared with in the FRB field, but FRB field is reduced by a factor of 40%. And this is in early years of the two fields. So GRB you can read off from the upper axis, and FRB can be read off from the lower axis. You can see scaled by a factor of 40%, they're comparable. And then the GRB field booms up, and I believe FRB number will continue to rise. This was a slide I presented 3 years ago at MG15. And back then I was comparing these two fields. They are addressing three same questions. Are they astrophysical? Where are they? And what make them? And it turns out that back then, I think FRBs were just localized. We knew where they are, but back then I put a huge question mark here. What make them is very difficult to answer. But 3 years later, so this is the same table, added one more column. Are there multiple types? So you can see the comparison between the two fields. They just went parallel, and the FRB field proceeds at the accelerated rate, because we actually answered what made them, at least partially, as Vicky just mentioned, at least some FRBs coming from the magnetars. So this is so amazing. And this field has been a lot of fun, as Vicky gave an excellent review from the observational aspect. So from the theorist perspective, we are doing a job similar to a detective. So we basically using the fingerprints, footprints, sometimes a smoking gun, and trying to figure out the crime scene. So this was the theory wiki page, which has been there for a while. I think it's there are 50 some models, but this was before the detection of the FRB from the Milky Way magnetar. And on this day, 2020-04-28, this event happened, and this completely changed the field. One of my colleagues joked that this was the collapse of the wave function, FRB wave function, because before this event, there are 50 possibilities, and now there's a confirmed possibility. But probably there are other possibilities as well. But we do know that at least some FRBs are produced by magnetars. From the model, theoretical aspect, any FRB model should be composed of two parts. If you look at the literature, you can see that all the models, they're actually talking about two things and then combined together. One is the source model. So this is the where the 50 possibilities actually came from, including repeating models, non-repeating models, catastrophic models. We still don't know whether these guys exist. But the other aspect is trying to understand how the radio waves are produced. So this is closely connected to the coherent radiation mechanism of the plasma. And there are two subtypes. One is inside the magnetosphere, the other is outside magnetosphere from the relativistic shocks. This one is more like a pulsar model, this is more like a GRV model. And there are many varieties under these general categories. Theorists can do this in two opposite directions. One is the bottom up. So one may pick up one of these models, one of the source models, one of the radiation models, and go upwards and trying to stick to this particular model and say, okay, this model can interpret a variety of the observations. When new observations come out, they will think hard how this model can reproduce the data. Pros and cons. The pro is that people can really, for example, there's a particular coherent mechanism, we can do a detailed numerical simulations, we can figure out all the detailed physics. The con is probably the FRB is simply not through this mechanism. There could be other mechanisms. And we all know theorists are stubborn and they are also highly competitive. A competitive theorist can make any model work to interpret any observations. So in this approach, then there turns out the risk that different people are talking about different things and they never can convince each other. The other approach is the top-down approach. So we start from the observations and ask ourselves, okay, what this observation really tell us? And then we go down to the branches and try to eliminate some of the possibilities and try to hopefully identify the correct mechanism, which is a difficult job as indeed. But my talk will try to go through this direction, top-down approach or the detective's approach. But since I myself is also a theorist, sometimes I will jump to the stubborn side and trying to discuss the bottom-up approach. Okay, so the talk is the physical mechanism of fast radio bursts, a detective's approach. So let's just forget about all the models and starting from some of the very basic observational facts and trying to constrain the physical properties of the sources. Vicky already touched some of these. The first one is just the duration. Based on duration multiplied by speed of light, we can get a size. And this size is the size of the central engine, which is 100 kilometers, essentially. So this argument actually comes from, say, this simple argument: if this is a optically thin region, and suddenly everywhere there is a impulsive emission from everywhere, just based on the propagation delay, the light propagation delay, there is a delta t, and this delta t is defined by the distance divided by c. In other words, this distance should be delta t times c. But this argument is actually did not consider the motion, especially the relativistic motion of the emitter. So actually, if the emitter is moving relativistically, in principle, this emission region can be much, much greater. It can be greater by a factor of gamma squared. But on the other hand, so this is the case actually for the relativistic shock model of FRBs. But this does not really change the constraint on the central engine itself, because the delta T in the emission region would be connected to another delta T from the central engine, which is much shorter. And these two are connected by a factor of gamma squared. And then from here to here, it decreased by a factor of gamma squared. So the observed time scale is roughly that time scale of the central engine. So this constraint actually immediately tells us that the source has to be something compact, like a neutron star or a stellar mass black hole. In the literature, there have been discussions about white dwarfs or regular stars or AGNs. So these sources are much larger than this. In order to have these models to work, one really needs to introduce some fine-tuned condition to make a small region of these objects to emit. For example, white dwarfs, we have to probably go to the polar cap. For AGN, we have to have some small blob. And for stars, we really need to have a very small patch. So this is the first constraint. So we need to have a compact object. The second constraint is energetics. So if we use the flux and fluence observed from individual FRBs, we can, based on the distance either directly measured from redshift or estimated from the DM, one can actually estimate the luminosity and energy, but these are isotropic ones. So we don't know the beaming. We can only assume that everything emitted isotropically, and we get these numbers. And as Vicky already mentioned, there's a wide range of distribution for both luminosity and energy. For the luminosity, it ranges from 10 to 37 to 10 to 46 ergs per second. For isotropic energy, it ranges from several times 10 to the 34. This is the globular cluster FRB Vicky just mentioned, and all the way 10 to 43. Let's talk about energetics of the source for one-off burst, if the burst just happened once, and what is, we know the energy of the observed FRB, but what's the energy of the source or the luminosity? So we need to do two corrections. Number one, we need to correct for the beaming, which means if the emission is beamed in the narrow solid angle, delta omega, then the total energy or luminosity should be smaller by this factor. On the other hand, we should also correct for the radial efficiency, because whatever object it is, for example, magnetar, it will emit something else. For example, the galactic magnetar radiate X-rays other than radio. So there's a radial efficiency factor. You need to divide by that. So this one tends to increase the energy, and this one tends to decrease the energy. For one-off burst, we can do this, even though we actually don't know these numbers. For repeaters, we actually care about the, so during the entire lifetime, how many energy is released, and on average, how much luminosity it is radiating. So besides worry about these factors, we have to also consider the burst rate. So number of bursts emitted per unit time, per unit energy range. We also need to worry about the duty cycle. For example, periodic FRBs. So they are quiescent during certain phases and active in some other phases. And we can eventually compare these constrained energetics to a certain source model. And those sources probably invoke magnetic energy, spin energy, gravitational energy, or kinetic energy. So this is the very general constraint one should place to any source models. The third one we can also mention is the brightness temperature, just based on the luminosity and the duration of the FRBs. One can derive something called the brightness temperature. This is not the true temperature. This is just, say, effective imaginary temperature, because if it is black body radiation, we know black body radiation luminosity is proportional to T to the fourth power and the area. And the duration actually gives you a characteristic length and an area. And then one can make a connection between the luminosity and the temperature. So these are the black body emission, and this is 1000K, 100K. And we are talking about the 10 to the 36K, way above there. So which means if FRBs are produced by cerebral radiation, the temperature is huge. But that is not the case. It just says that there's no way to produce this incoherently, because any radiation mechanism will undergo self-absorption. So this is how this radiation regime developed. In order to avoid that, we need to come up with some coherent radiation mechanism, which in the literature, there are three broad types. The first one is just like the antenna for TV. So we have electrons moving globally, coherently to emit as bunches. So instead of each particle, so the emission power, instead of we're talking about individual electrons, we are talking about a group of electrons bunched together as a huge charge and let it emit coherently. And the second type is the plasma maser. So because we know that emission source must be plasma form, and the plasma have certain instabilities. There are some oscillations, some wave modes. They can grow as a function of time. They can reach to very large amplitudes, and eventually that oscillation will, that electromagnetic wave in plasma can be converted to electromagnetic wave, essentially in vacuum, propagate all the way to Earth. The third one is already electromagnetic wave, but they travel, they call vacuum maser, but not exactly vacuum. There's still plasma in front, but there's a negative absorption. The emission will continuously get negatively absorbed, which means amplified, so that one can reach a very high brightness temperature. And this plot actually shows that all different the astrophysical radio sources. So this region is the incoherent radiation regime. You can see the brightness temperature goes up in this direction, and FRBs are at the almost high, at the highest, and radio pulsars are slightly lower, some of them are comparable. So that is the third general constraint. The fourth general constraint is about the absorption processes. So in order to have the radio waves to reach Earth, we have to avoid some absorption or scattering processes. One is called induced Compton scattering. So this optical depth drops rapidly with electron Lorentz factor, and bulk motion can also help to reduce the optical depth. And for free absorption, as we already mentioned, if we are in a hot, dense medium like a supernova remnant, and initially the radio waves just cannot penetrate through. It takes time for the supernova shell to become transparent. For synchrotron absorption, so if some sources are likely surrounded by some persistent source, which could be powered by synchrotron, And that synchrotron nebula could also absorb the FRB emission. On the other hand, some of the absorbed FRB could heat up the nebula. So these are the general processes that limit the detection of FRBs. We need to worry about this in theoretical modeling. The fourth one is we can observe a lot of interesting properties in polarization, and most of the FRBs are highly linearly polarized. Some of them are close to 100% in terms of linear polarization. And one can also look at the evolution of polarization angles across the burst. Some of them are constant, some of them are varying. And with polarization, we can measure how that polarization angle evolved with frequencies. That's a so-called Faraday rotation measure. And it turns out that a lot of FRBs have quite large Rn. So all these actually suggest that the emitter and even the nearby environments has to be strongly magnetized. Especially in the emission region, we actually require ordered B field. So in any case, and because we don't know how FRBs are produced, people usually appeal to two neighboring fields, the gamma bursts and radio pulsars, because we more or less know how the emission are radiating those sources. So the lesson from the GRB field, for many years, people have developed this relativistic shock model, including both internal shocks to produce gamma rays and external shocks to produce afterglows. And actually, such kind of picture was borrowed to interpret the FRBs with some addition. So in the GRB shocks, they are not magnetized. For FRBs, because, as I said, polarization requires ordered magnetic field. So usually these shocks, not only they're relativistic, they're also magnetized. People need to introduce ordered B field in the shocks and start to make the electrons to emit coherently. Some mechanism called synchrotron masers. Actually, they are cyclotron, close to cyclotron and close to bunches instead of masers. But this is a name people have been using all the way. So there are many authors discussing these mechanisms. And another one that's from the radio pulsar community, people have been trying to understand the coherent radio emission from the magnetosphere, either from the inner region or somewhere in the outer magnetosphere close to the light cylinder. And in the pulsar field, there are also inner and gap, inner and out, inner gap and outer gap, or slot gap, or sometimes it's slightly outside the light cylinder, the current sheet region. It could be another site. So as a result, for the FRBs, we have two competing models. So one is the pulsar-like, the other GRB-like. And in particular, for this 2004-28, the galactic FRB, these two models have been discussed to interpret a variety of the observed properties. So for the so both models invoke a magnetar, and we need to have a magnetar to do something, probably a cross cracking and send out some alpha waves, can heat up the magnetosphere, make X-rays, and then there could be a probably open field line region where particles can actually come out and eventually make radiation, coherent radiation somewhere. These two models have different predictions in terms of beaming angle. The pulsar-like model, because we're talking about a magnetosphere, they're likely narrowly beamed. And the GRB-like model, because it is outside the magnetosphere, and for magnetized jets, there's little collimation. So very likely this magnetized relativity shock are wider. In terms of radio efficiency, pulsar-like models have a relatively high radio efficiency, which means have slight, relatively less energy going to high energies. But for shock model, produce more energy actually in the high energies. So this is related to brightness of the high energy counterparts and the polarization properties. This is very interesting. Both models could in principle produce near 100% linear polarization. But in the pulsar-like model, it depends on where the radiation region is. If it is close to the polar cap, then one probably can make polarization swing, just like what is observed in radio pulsars. If the emission region is far out, and probably you see straight field lines and the polarization angle would not change much. But for the shock model, because we are talking about the parallel B field in the shock plane, it is hard to produce significant variation, especially sudden changes in the polarization angle. So this is the top-down approach. Observationally, we do see that for repeaters, the first repeater, actually, their polarization angle is constant, but some non-repeating FRBs, one can see these jumps of polarization angles. So as I said, for this constant polarization case, one can do it in both the shock model and the magnetosphere model. But for this one, likely we need magnetosphere model to do this. And even for repeaters, actually this is a repeating source, another repeating source, one can see that polarization angle can change significantly from burst to burst. This one going up, this one going down with some dips, and all these complicated behavior. It is more reasonable to understand within the magnetosphere model, but it's hard to do it in the shock model. Another constraint from the observation is the burst rate. As Vicky already mentioned, for 121102, FAST detected more than 1,000 bursts within a time span of less than 2 months. There's a distribution of numbers as a function of energy. There's also distribution of the waiting time. You can see there's a very high repetition rate and short waiting time. Sometimes you have, after milliseconds, you have another one and continue to do this on and on. This actually places some constraints to the models. For example, if your trigger mechanism is very expensive, then you cannot do this. This is very frequent. You can do it like in milliseconds, or there's a long, characteristic waiting time for about 100 seconds. You need to generate a lot more. So some of the models just cannot do this. Another thing is one can place the constraint on the energy. For example, if it is the shock model, because the efficiency is very low, it means that a lot of energy goes to high energy, then the energy budget is high. The 47-day burst for this particular event already used up about 1% energy of the magnetic energy. So that is quite expensive. But for magnetosphere model, this number becomes smaller. I should also say it is not public yet. FAST, we detected another very active source, actually the chime source, and we detected more than 1,000 bursts from that one as well, with similar properties. Okay, so this is the Seth-Schoenbaum effect Vicky mentioned, which means that arrival time of the lower frequency waves arrive later. Then there's a question how to do this. In the magnetosphere model, actually it's quite straightforward, simply because in the pulsar magnetosphere, we already knew something called the radius to frequency mapping, which means that different frequency actually emitted from the different heights. So as suppose there are some blobs or bunches emitted from the neutron star and trying to move out in different field lines, as your line of sight sweep across the beam, the one you see earlier must came from a lower altitude, and as time goes by, you see emission from a higher altitude from a different field line with a lower frequency. So within this model, it's quite straightforward. Within the shock model, you can also do that because at a later time, probably the shock front propagates to a larger distance and B field goes down. The difficulty is the recalibration for the shock model. For neutron star, there's always a surface. You can every time start from there. But for shocks, yeah, it could happen especially for wide distribution of time, so separated by months. So we don't know whether the collision will happen around the same radius every time. Okay, this is the periodicity. Vicky mentioned time discovered the 16-day period and also has the frequency-dependent model. And in the literature, there are 3 models. So one of them talking about the magnetar period of this long, which is quite far-stretching. The other 2 models invoke the binary orbital period or the precession of the magnetar. And this frequency dependent window ruled out that this is due to eclipsing in the binary system. That is for sure, but it does not rule out the binary scenario. So I'm jumping back to my theorist approach, the stubborn part approach, because myself developed this. So actually, we have a recent model saying that actually the eclipsing is very actually straightforward to interpret the arrival of high frequency bursts earlier than low frequency ones. It is a matter of how they disappear later. So that must be related to the emission mechanism. For example, if it is magnetic origin and they coming from different altitudes, one can do that. This has been discussed by Dongzi in a recent paper. Okay, so next subject. So we all know that there is a FRB magnetar association, well known, but there's also a FRB SGR burst non-association. Actually, this we have been using fast to do long-term monitoring for this event, and during an episode, very active episode, we did, well, Fermi detected about 30 gamma ray bursts, but there's no radio emission at all, not FRB, not even a radio pulse. So this is quite constraining. And several possibilities could be due to narrow beaming, due to narrow spectrum, or maybe that SGR burst is very special. There are already several papers pointing towards this possibility. But the beaming is also one interesting possibility. This one is essentially ruled out. So if it is due to beaming, then one should expect to see some of the events off the axis for the galactic magnetars. For cosmological FRBs, these probably are too faint to be detected. But for the galactic magnetar, we could see this bursts which have a wider or slower width and lower flux. So I call them slow radio bursts compared to fast radio bursts. And there is a so-called closure relations. The luminosity of these guys should be related to the luminosity of the FRBs, or the flux should be related to the FRBs, and the width should be also related to FRBs through certain closure relation. It depends on the intrinsic spectrum of the FRB. So if the observational frequency is the same, so basically we have this simple relation. If it is a power law, if it is a Gaussian, then it becomes a little bit more complicated. And there are several actually fainter, slower bursts detected already, but only 1 or 2 seems to be consistent with, but a lot of them are not. But this is very interesting test, we have to search for slower bursts from these events and trying to match these conditions and see whether or not they are off-axis FRBs. In that case, one can really confirm this beaming hypothesis over FRBs. Okay, the open questions. There are more than 3, but I list the 3 interesting ones. Where is the FRB emission generated, whether it is magnetospheres or shocks? So, and what is coherent mechanism? So this one, it is still subject to hard debate, and I believe, especially the second part, what is coherent mechanism, it will take time to get it. Are there engines other than magnetars that power FRBs? If so, what could be the plausible sources? I'll discuss this one in the next slide. Are there genuinely non-repeating FRBs? If so, what could be the plausible sources? This is also very interesting. Time will tell. So these are the 2 extreme versions of the source models. Besides magnetars, what can we have? So this extreme is saying that all the FRBs are produced by magnetars. We have regular repeaters produced by regular magnetars. This is assuming that there's no non-repeaters. So all the FRBs are repeaters, so just some of them, just the repetition rate is too low, and they're all produced by regular magnetars. And there are some active repeaters. Those active repeaters probably are produced by special magnetars, probably born from the long GRBs or neutron star mergers or superluminous supernovae. They are rapidly spinning and younger. So this is the one extreme view. The other extreme view, I think, it could be more exciting, is that besides magnetars, we have other things. For repeaters, we have magnetars, we have some other things. And we have non-repeaters, intrinsically non-repeater, they're probably related to compact star, combined binary coalescence, blizzards, and other things. Probably the reality sits somewhere in between. They're probably not like 50 different ways of making FRBs, but if there's just one way to make it, we probably underestimate the creativity of nature. So somewhere in between is what we would expect, but it takes time to find out. Vicky also touched this globular cluster FRB. So it is very interesting. So the distance is 3.6 megaparsec, very close, and it's sitting right there in a globular cluster. And in terms of energy or luminosity, so it is actually even lower than the galactic FRB. So they're quite moderate bursts. They're bridging the gap between the radio pulsars and the cosmological FRBs. Then question is, do we have a magnetar there? As Vicky said, magnetar in the globular cluster environment, it's hard to have young stars. You can use double neutron star to merge to make a magnetar, but most of the K mergers will probably make a short-lived magnetar lasting for hundreds of seconds or just 1 second and collapse into a black hole. One can probably argue for accretion-induced collapse of white dwarfs, white dwarf mergers. Those possibilities are open. But I'd like to discuss another possibility. So this possibility actually was published last year before knowing this. I think it could be a promising candidate. Instead of having a post-merger magnetar, we are talking about 2 neutron stars spiraling in. And if we really work out when these 2 magnetospheres start to interact with each other, we find that it happens actually decades, centuries, or even thousands of years before the merger. And because the energy budget is pretty small for this one, so I think even for this minor interactions, one can already probably produce these repeaters. So these are the estimates of the energy of the system. So eventually, the FRBs are produced through, say, reconnection or dissipation of the magnetic energy, but the magnetic energy can be replenished actually coming from the spin energy of the stars. So, and the spin energy of the both neutron stars are plenty to power these. Something like the solar magnetic cycle. So every round there are magnetic dissipation, and after that the sun goes to quiescent state, but from the rotation energy you can tap more magnetic energy, and after a while it will produce a burst again. So these guys could be relatively abundant in globular clusters, and the time scale is much longer than the say the post-emerging magnetar case. And this model actually predict that these sources could become more and more active as a function of time, because the two become closer and closer, and there are more and more dissipation happening. And very interestingly, these guys should be millihertz gravitational wave sources, because they're at that distance, they could be detected, especially at this small distance, they could be detected by LISA, Taiji, Tianqin, some space-based gravitational waves after they are launched in 2030s. Okay, so I think that's all. I summarize my talk. For coherent emission models, there's a debate between location, magnetosphere, and shocks. And it turns out that at least from the top-down approach, the current data supports a magnetosphere origin for at least some and probably all of the FRBs. And source models, the most conservative ones, magnetars do it all, and the most speculative ones, there are many different types. The prospects observationally probably will detect the galactic FRBs more with CHIME and STARE2 and other detectors. Maybe next one also come from magnetar, maybe not. Maybe they come from something else, and then we know that there are other FRB sources. Multi-messenger observations can hold the key to identify or eliminate models. For example, the scenario I just mentioned, it could be in principle detecting gravitational waves. And from theory aspect, the debate on the coherent mechanism will continue if the pulsar field could be any guide after 60 years, people are still debating which coherent mechanism. I believe this should be also the case for the field of FRBs. And for the source, the magnetar, how magnetars make FRBs, there are already been a lot of studies. I believe there will be a lot more. And also the physics of other systems, of course, with the observational breakthrough and the study of other systems will become more hotter topic. Okay, I'll stop here and take questions. Thank you.
We have questions. Well, first of all, let me thank you for this very informative presentation. As beautiful and interesting as the one of Vicky Caspi. You made a good team. Now, let's see if there are questions.
Yes, I would have a question. I'm Jenny Wagner, and I would like to ask, what can you learn from the de-dispersed resolved pulse shapes? So, for instance, from the CHIME catalog, which has been recently released, about the sources and the emission mechanisms. So when you see the intensity over time in the de-dispersed regime.
Yeah, that is a very good question. So if we see multiple pulses within a burst, this within the pulsar-like model, one can actually try to diagnose into the emission beam, say what kind of field lines are making radiation. So with more and more data, probably one can try to map something like a radius to frequency map or something. But for the shock model, one needs to really answer within this short period of time, because the shocks are consecutive. So with one collision, you produce a synchrotron laser. and that plasma is already heated up. When another one comes in, should be a prediction that, for example, the degrees of coherence, those kind of things have to change according to a certain pattern. If this is not observed, then in the shock model, one really needs to argue for some independent collisions. For example, even though we see like 3 pulses overlapping each other, they have to say that, okay, we have 3 collisions at different locations. Of course, with that freedom, they can interpret everything, but it is less elegant. You basically kick the ball back to the central engine and ask the central engine to do whatever trick to produce the data.
Thank you very much.
Thanks.
Another question from Shashank, please.
Oh, hello. What's energy spectrum of the FRB look like?
Yeah, it's a very good question. It is not well measured, but early on, if we really assume that they are power law spectrum, then it turns out that spectral index varies significantly. For 121102, some bursts have like negative 14, some others have positive 10. So that actually already hints towards a very narrow spectrum. Actually, from the CHIME observation and other telescope observation, one can see that FRBs are detected not in the entire bandwidth, actually in a certain bandwidth. That points towards something like a Gaussian-like or even line-like emission, at least for some of the FRBs. I believe, Vicky, correct me if I'm wrong, for repeaters, they are more narrower and looks like more line-like, and for non-repeaters, it's more like power-like. Vicky, am I right?
Yeah, that's definitely true. There's complex spectral structure in repeater bursts. Not all repeater bursts, but in most repeater bursts. And there's definitely a different population that seem broadband, at least as far as the bandwidths of any one telescope show.
Seems there are no more questions. So maybe we can thank the speakers of all this session again. Thank you very much.
Thank you very much, both of you.
Thank you.
Thank you very much.
Now we are starting the roundtable on the particular JRD source 170817. And we have 2 talks scheduled. So the first talk is by Eleonora Torria. Could you please share your screen, Eleonora? Yeah, we can see you.
Yeah, well, yeah. 1 second, I will. Okay, let me see. Okay.
Abbassa la cosa, non si vedono gli occhi.
Ora si dovrebbero vedere le slide.
Perfetto, perfetto. No, ma anche te.
No, non so bene come farlo funzionare sull'iPad. Beh, iniziamo, non perdiamo tempo. I was asked to review the current status of the X-ray observations of GW 17017. So I would like to thank Remo for inviting me at this very interesting meeting. I'm sure you all heard already many talks about this source. I will start with timeline of this event, summarizing the most important moment of the discoveries. Initially, as you can see, we had the merger discovery by the gravitational wave observatories. And this was followed by rather weak gamma ray burst of a short duration, which was discovered by Fermi and also detected by Integral. You see in this picture the correlation between the merger signal and the gamma ray signal, which peaks 1.7 seconds later. So this signal was not only temporally close to the merger event, it was also in a location in the sky that is consistent with the localization provided by the gravitational wave observations. You can see in this plot in pink red, you see the Fermi localization, and here in green, you see the localization of the gravitational wave transient. So for this reason, because of the temporal and spatial coincidence, we thought the two events were indeed associated and coming from the same system. And what was even more exciting for observers is that the volume enclosed by this gravitational wave event was very small. So you can see the area in the sky was a few tens of square degrees. And also the distance was approximately 40 megaparsec. So looking at the number of galaxies that could have hosted this event, we did not have much choices. And this is good because there were at most 50 candidates that could have been the host galaxy of this transient event. So what happened is that many telescopes around the globe started to observe. Either they cover the full area of the sky, localized by LIGO and Virgo, or they targeted these dots, which are the galaxies candidate to host the gamma ray burst. And about 11 hours later, we had the first report of a possible counterpart, which was a very bright optical source that you see here located in the inner regions of an elliptical galaxy, NGC 4993, at about 40 megaparsec. And what became really interesting is that a few hours after the optical detection, there was a swift observation, and Swift reported the lack of X-ray emission. And this, for us, was really the first sign that we were not looking at a standard afterglow because of the bright optical UV emission and the deep limit on the X-ray observations at early times. We understood this was probably a thermal component, very different from a GRB afterglow. So the afterglow itself came up later, a much later time, and the first detection of the afterglow was carried out by my team with Chandra at 9 days after the merger. And you see here the Chandra discovery image. What you see here at the center, this bright source, is the galaxy nucleus. And here, this is the location of the optical infrared transient. And at the same location, we see this red dot is the X-ray counterpart. So it came at the very end, and a week later, radio observations carried out with the VLA also uncovered at the same location radio counterpart. And so this gave us an indication that this X-ray and radio were probing a different component of non-thermal emission. So now that we are nearly 4 years after the event, we can see here the evolution of the X-ray emission. you see at the center, this is the field of the transient, and you see at the center there is this bright nucleus. But you can also see in this stacked image, we can resolve that there is a diffuse soft X-ray emission in which the transient is embedded. And here, a 10 arcsecond from the galaxy nucleus, you see the X-ray counterpart. And in the stamps that you see here, you can see the temporal evolution of the transient. You see at 2 days, there was nothing detected by Chandra. The first detection was this weak but significant source at 9 days. And then very surprisingly, it did not fade like all the afterglow seen by Swift, but it became brighter and brighter. So you see at 100 days, it was 5 times brighter. It reached its peak at 160 days. And then after that, it started to decay really fast. You see, at 1 year was faint again. But with great surprise, you know, after this point, the decay became, I would say, shallower than what we expected. And indeed, we're still detecting this source at 3.5 years after the merger. You see, it's weak, but thanks to Chandra, we can still claim a significant detection. So here, I show the temporal evolution of the non-thermal component that we observe in X-ray, in radio, and at late time also in the optical range. And the salient features are, first of all, this initial rise of the emission with a slope of about 0.8, which is quite shallow. Then we have this peak at very late times, 160 days, and then a steep temporal decay with a slope of about minus 2.1. And so if we look at the spectrum of the source, this is a remarkably long-lived power law. You see from 15 days up to 1 year, there was no spectral change. And we can see that the radio, optical, and X-ray data all belong to the same power law component. And so if we interpret this as synchrotron emission, so my apology if the symbol are somehow they changed, moving the PowerPoint to the iPad, but you can see better in the figure the regime of synchrotron emission that I'm referring to. So what you see in this panel here is the typical spectrum of a gamma ray burst. And you see that in this particular case, for over a year, we were probing always the same portion of the spectrum. So this was a bit, you know, it didn't allow us to constrain all the parameters because we were always probing the same portion of the spectrum at all wavelengths. But it allowed us to constrain really well the spectral slope.
Domattina, quando vieni alle 9.
So the spectral slope, as you see, is constrained really well. We measure an electron spectral index of about 2.17 with a very narrow error. And this is perfectly consistent with the distribution of a spectral index inferred from gamma ray burst afterglows. So from this observation, really, we can't say this is a special afterglow in any possible way. Two keys observation that allowed us to show that there was a relativistic jet in this object, where first of all, this high resolution radio imaging. What you see in this case is the position of the radio emission at 2 different times. Sorry. And you can see how the centroid of the radio image of the afterglow shifted with time. So this is at about 100 days, and this was about 200 days. And because of this shift of the centroid motion, we could derive that the source was moving at a relativistic speed. And so this was the first evidence for a relativistic jet. Radio imaging also allowed us to measure the shape of the image, and this is consistently a compact source. So this allowed also to exclude all those models that were predicting spherical emission. Another important clue that came from the temporal evolution of the afterglow was the late time decay. So this is important because, you know, in this particular case of 17817, we were really lucky that the source was bright and nearby. So high resolution radio imaging was possible, but in the future, we do not expect to be you know, so lucky again. So future events could be much fainter. And so radio imaging might not be possible. And in this case, you know, a very important alternative is the temporal monitoring of the source. And so what you see here is the comparison of the data set at late time. So this is the post-peak evolution from 160 days up to about 1.5 years. And you see how the data follow really well this blue curve, which is the prediction for a relativistic jet, which is supposed to decay really fast after the peak, while all the models predicting a more isotropic spherical outflow also predict a much shallower temporal decay after the peak. And so by monitoring the afterglow at late times, we were also able to discard these models with high confidence and also confirm the presence of a relativistic jet in agreement with the radio observations. So I would say that after this set of observations at late times, I think many people converge on this picture that the non-thermal component that we observed in radio and X-ray was produced by a relativistic jet. And this jet was, first of all, it was not seen down the barrel of the jet. So we were not looking down this orange axis, but we were slightly shifted at an angle of about 20 to 30 degrees. And the additional feature that observations revealed to us is that this jet had to be surrounded by some sort of wings or cocoon, as people call it, of material that is less energetic and less relativistic. So at the very beginning of the observations, we were watching the emission produced by these lateral wings. And then as time passed, the relativistic jet was decelerated and it started to open up. And so only at late times, our observations started to probe the core of the jet. And so this is the picture that we had after 1 year of observations. So what I want to show here are the comparison between the, and I'm sorry again, I think some of the plot were changed in the conversion, but I will try to explain. So what I'm showing here is the comparison of the model with the data constraints. And you see on the left, these are the constraints coming from the temporal evolution of the afterglow. And this dotted line is the afterglow model from a structured jet. The viewing angle is about 20 degrees. And you see that this model fits really nicely the temporal, the light curve. And then what you see on the right, these two data points are actually the measurements of the centroid motion from radio imaging. And what you see in blue is the prediction from the model. And this is the 68% contour that you see here in dark blue. There was supposed to be a 95% contour also, but it's not visible, but it's about here. It's a bit larger. But in this case, it doesn't matter because you see how the model prediction fit nicely all the observing constraints. And this is about at 1 year. So at this point, our idea was that this was a quite ordinary jet from a GRB with parameters that are completely consistent with the afterglow parameters of short duration gamma ray bursts. And at this point, things started to deviate from this simple prediction. And now I want to show you what is the status of the observations right now. So you see here again the same figure, but with the updated data set of collected over 3 years after the gravitational wave event, the gamma ray burst. So what you see on the left is again the afterglow light curve. This point in black are the X-ray data point. This point in blue are the radio data, just shifted to match the X-ray normalization. But you see the temporal behavior is more or less the same. And you see how at the late times, these last few observations are systematically brighter than the prediction of the jet model that we made after 1 year. And so in order to account for this brighter emission at late times, we need to change some of the afterglow parameters. And so you see how, this solid line is the model of 1 year, and you see how it underpredicts the emission, both at X-ray and radio wavelengths. And the more data we collect, the more our model needs to be fine-tuned. And what happens is that in order to account for this late time emission, our viewing angle is changing. So is shifting from about 20 to nearly 40 degrees right now. And this is not surprising because we know that with the temporal monitoring, we actually can constrain the ratio of these two parameters, the viewing angle and the jet opening angle, which is about 6. And so this is coming from the temporal monitoring, but luckily we have another constraint, which is the centroid motion. And this allows us to place much tighter constraint on the viewing angle. And so as you can see, what is happening at this point is that the jet model with large viewing angle of about 40 degrees can reproduce the late time X-ray observations. So they can reproduce this bright emission, but it starts to underpredicts the motion of the centroid. So we are, it's still not a large discrepancy, but definitely we are starting to see a tension between the late time observations of this transient and the simple jet model. And one thing that I wanted to clarify is that, there were claims that, this last data point was, evidence for this rebrightening of the X-ray emission. I would like to know that this is just a small deviation from the model. And instead, what, the evidence for attention between the jet model and the data is not coming from this simple last observation, but it's really coming from this persistent trend that we've been witnessing for several months right now. And this type of shallower decay that is driving the viewing angle toward larger values, and therefore is creating this tension with the radio imaging constraints. And so the reason of that is not clear to anyone, it's not clear to me, but it's definitely opening up new possibilities to study this source. You know, now that the jet is fading away, we may be able to detect a new component. So one thing that I wanted also to emphasize, that while in X-ray we have significant and I would say a robust detection of the X-ray emission, in the radio the signal is really marginal. You see here the position of the transient is marked by this white circle, and you see here there is some signal, but we are talking really about it's at the level of the noise of the image. So it is still not clear whether the radio emission is following what the X-ray is doing or not. So I would say these last observations are really driven by the X-ray detection. And so as I was saying before, we have several possibilities open in front of us if this behavior continues to be detected. And this, what I'm showing here is actually a prediction that was made in 2019, suggesting that, you know, if the central engine of this object is still active, as it could be if it is, for example, a massive neutron star, then we should see a flattening of the observed emission. And this could be either at X-ray wavelength only or at all wavelengths. So different models make different predictions. But depending on the evolution of the emission, we could be able to test this prediction. And of course, let me point out that the implication of that would be very important for the equation of state of a neutron star. Because thanks to the gravitational wave data, we know the mass of the system. So if this was really a massive neutron star that was able to survive the merger for such a long time, the implications will be really important for our understanding of these objects and their equation of state. But there is also another realistic possibilities, is that we are seeing an afterglow, but this time not from the relativistic jet, but from the subrelativistic ejecta. So we know that these slower moving ejecta were there because we saw the kilonova. And from the optical and infrared observations of the kilonova, people derived that there was a large mass of ejecta moving at speed like 30% the speed of light. And indeed, based on these measurements, we can predict the type of signal that we expect when these ejecta interact with the surrounding medium. More or less as it happens, for example, with ejecta of supernovae that at late time rebrighthen in the radio band. So in a very similar way, we could see a rebrightening of the emission at radio and X-ray wavelength. These are some predictions that we made based on the kilonova observations. And you see there is a wide range of behaviors. So it could remain flat, but it could also rebrighten substantially. One thing to notice is that the time scale will be really slow. So it's going to take a long-term monitoring of this event to really distinguish between these different possibilities. But again, the implication for this will be very important. What I wanted to show here is that, based on simulations, we know that many of these mergers produce a large amount of ejecta, and most of these ejecta have velocity of about, let's say, 20–30% the speed of light. And this is what we probe with optical and infrared observation. So when we observed the kilonova in 2017, we probed this mass of ejecta. What we did not probe is this tail of the distribution. So the presence of this tail, of course, depends on the merger dynamics and the equation of state of the neutron star. But it seems to be quite a common feature of the simulations. And it predicts different slopes of the distribution depending on the details of the merger. And so all these, fast-moving ejecta are not observed when we observe the optical and infrared emission, but they can be probed through this late-time X-ray and radio observation. Basically, the profile of the ejecta distribution, the velocity profile of the ejecta, is going to shape the light curve of this late-time radio flare. So from the rising part of this light curve, we could derive what is the slope of this distribution. So this would be a very novel measurement that we could do, but also in this case, it will require some time. So here we made some predictions based on the model. These were made a year ago, so this was 2.5 years after the merger is the orange curve, and you see that at that point, basically all the index had equal probability. But if we keep detecting the X-ray emission for, let's say, 1 more year at the same level of the current detection, then we can already place some constraints and say that our observation really favored the steepest slope of the velocity distribution. So I will now conclude my talk, and I just wanted to emphasize how X-ray observations were critical in the observations of this electromagnetic counterpart. And this is because they could probe really the faintest stages of the electromagnetic emission, and no other telescope was really capable of probing that. At the very beginning, X-ray observations discovered the non-thermal emission at 9 days, and the monitoring of this component allowed us to understand that there was a relativistic jet produced by the source. At the very end, now that the jet is fading away, this late-time X-ray monitoring may betray the onset of a new component, and this is a really exciting possibility. The origin of this component could be either a long-lived central engine, for example, a long-lived neutron star, or it could be this new type of transient emission arising from the kilonova ejecta. So only new observations could tell us the difference. Thank you.
Thank you very much, Eleonora. Beautiful presentation. Now we will hear, I think, the presentation of Jorge, where he will present a point of view which we presented already 3 years ago, but in the meantime, it has been improved and more detailed. Just to make sure, I don't know if I know that in the official presentation of LIGO, it was said that they detected first and then Fermi and integral after, but just to make sure, just to make sure to keep the real behavior, is that the first identification, we had a lot of discussion and they are still ongoing. The first identification was from Fermi and integral, and later on there was the purported detection prior, but with the human intervention, which showed that the LIGO had a signal before. But this matter is very delicate, and I don't think it's appropriate to discuss this, because this deserves a special meeting, and let's instead focusing of the physics of this very nice object that you have present, namely the GRB 170417A, and let's proceed.
Thank you very much for the introduction. So yes, I will just to start in recalling, as Professor Ruffini just mentioned, that this is an ongoing work based on our first analysis and prediction of this source in this paper of 2 years ago, which was about electromagnetic emission of white dwarf binary mergers. So it's very intriguing that as I'm going to show that GRB 17 or A17A for us looks very much as a white dwarf binary merger rather than a neutron star merger. So I will shift to the presentation. So, okay, I suppose you can see it. I will hide this thing. Okay, so let's move forward. This is some picture from, actually we published 2 papers about this source. So the first one was a pure observational comparison of GRB 17 or A17A with other short GRBs, which were supposed, so we have been associated with compact object mergers. But this is nothing new now. After 3 years, we know that in many properties, this GRB is special, or let's say different from the other short GRBs. What is more impressive from our point of view is the energy which has been measured to be released in GRB 17 or A17A, which is just of the order of 10 to the 46 erg with respect to the highest energy measured in short GRBs, which goes all the way to a few 10 to the 53 erg. So it's quite a challenge to try such a huge excursion of energetics with the same model. I mean, if you try to apply a neutron star merger to all of these sources, then you have to explain how the same objects, and you have neutron star merger, you don't have an scaling, for example, in mass. I mean, it's not that you are applying a model to a stellar mass black hole and to AGNs when you have a huge excursion of 8 order of magnitude in masses, for example. If you are using the same model, so roughly same masses of the merging components, if you try to say continue to, I mean, that's really a challenge from some same, have these constraints which are from the physical model itself to cover 8 order of magnitude of differences and in energy. So we prefer to think, and we started from the beginning to think about it, to see whether these kind of sources, which has low energetics of the order of 10 to 46 erg, are not neutron star merged, but instead they could be white dwarf mergers. So this is what this plot is saying. Here you see this are the gamma rays observed by Fermi of GRB 18 or 17A with respect to or the typical short GRB, for example, 093510 and other sources. Let's move. So I'll move fast. We'll keep the presentation simple. So our proposal was a wide door merger. So these are snapshots of our simulation that we made 2 years ago as a prototype example of this kind of system. So this cannot be only applied to 17 or A17A, but many other transients that we could see, or high energies, or with systems with these kind of features that I'm going to show now. So as in the case of any merger, what you see, what is important for us here are, and maybe see I have here this, what is important for these simulations, the formation of a new object here, which is the generate, so it's a high dense object. And the other feature which is important for us is the matter which is expelled, the ejecta from the merger. So just mentioned, so you have format the generate central remnant. This is a Newborn white dwarf that can be stable or can be metastable. It depends on the merging component. So you can have a sub-Chandrasekhar white dwarf or a super Chandrasekhar white dwarf. In that case, will be short-lived. In the case of the stable, it can be long-lived. And that's the case we are going to adopt here for this source. And the central remnant is fast rotating. So fast rotation for a white dwarf, we are speaking about rotation periods of the order of 1 and 10 seconds. And the magnetic field of the white dwarf can be all the way to gigagauss. And this is not nothing new. I mean, we observe white dwarfs with magnetic fields up to gigagauss. So, and the ejecta are typically of the order of 10 to minus 3 solar masses. This is not because we observe that the ejecta from a white dwarf mergers, but because this number comes from a numerical simulation. And so I'm going to show from the analysis of 17 or A17A, it turns out that 10 to the minus 3 solar masses is exactly what you need to explain the afterglow of this source. So these are the ingredients and the physical process that work in this model. So I mentioned the degenerate remnant is to be highly degenerate, so it's massive, but still sub-Chandrasekhar object. So it's printed with a mass between 1.1 and 1.3 solar masses roughly, and then fast rotation I mentioned, and magnetic field. The expansion velocity of the ejecta, okay, the third point here, which I mentioned already, the first two, the third point, it's a speed expansion of the bound matter is of the order of 10 to minus 2 the speed of light, so 10 to the 8 centimeters per second. And since you have this newborn white dwarf, which is massive, fast rotating, and highly magnetized, then very likely you have this injection of energy from this central engine. It will be a central source which is powering the ejecta, and this goes very, very much into the lines mentioned by Elena in her last 2 or 3 slides. But this is not new. Actually, this was this kind of energy injection and the appearance of this central object. We predict that in our 2 papers of 2018 and 2019. So this is about the central object and the ejecta. So, but what are the physical processes that will lead to the emission? So, of course, we have a pro-emission into gamma rays in this object. So that could be a magnetospheric flare. So it is relatively simple to make a back of the envelope calculation or estimate of the energy that you have to do for emitting magnetospheric flares, and it turns out to be exactly of the order of 10 to the 46 erg for a magnetic field of 10 to the 9 Gauss in the magnetosphere of the emerging neutron star, the white dwarfs. And then Of course, this magnetic flare, it had to expand, and this is possibly, this is in our model the only component which is could have a relativistic motion. So is the only part of our model which has a Lorentz factor larger than 1 than unity. The early afterglow is the optical emission of the kilonova. I'm going to show for us is only this thermal cooling. So here we have ejecta from a white dwarf merger. So we don't expect it is our process elements, and therefore there is no decay from our process elements, but it's just the thermal cooling of the ejecta, which is this ejecta, as I mentioned, is powered by the central object. Then the late afterglow is consistent with a synchrotron cooling and the white dwarf pulsar emission. So you will find that some of these, this model have some share some properties with the model of that in Elena's presentation. Of course, with the difference that here we are speaking about white dwarf mergers and non-neutron star mergers. These are the typical light curve. So this is not a fit of the sort. This is just from some typical parameters of this model. So here I show what would be the emission expected from 10 to the 9, roughly 10 to the 9 Gauss white dwarf with a period of the order of 3 seconds. In injecting energy into this ejecta expanding at 0.01 C. And so this helps you see some features, some cures here in the gamma rays. So from 30 MeV, these are, I show some bands which are typical of the instruments that observe GRP. So we are here. So we are here at Fermilat, Agile, here with Fermi GBM, here is SwiftAxer-T, and then you have the optical emission in the R band. You have the infrared, and the infrared at a Hubble Space Telescope band is this blue one. Then I'll show here also this is the radioluminosity of 15 gigahertz, and then you have also the white dwarf pulsar. White dwarf pulsar is just this magnetic braking emission, so typical pulsar emission that we here you see this as a flat. Is just because the characteristic spin down time scale here is longer than 10 to the 7 seconds. So still you see just the power flat. And then I just plot here this thin red curve. See, that is the sum. So of the synchrotron in X-ray and the sum and the pulsar luminosity. So this is what we predict. Was the possibility that we advanced 2 years ago that this the white dwarf pulsar could emerge around this time and produce a flattening of the X-rays. So these are or typical light curve. These are typical spectra. This is as a function of time. So you see there is a typical hard-to-solve evolution here. But they are essentially they are synchrotron spectra. This is instead the fit, the fit of a specific fit of the source of GRB 1708, 17A. So let me try to specify here some of this data. So here we have the points in the 0310 keV band. These are X-rays. While here we have, these are the kilonova points, these orange points, the R band. Here we have the infrared in the HST band, HST measurements over there, and then we have here the radio emission in at 3 gigahertz and 5.5 gigahertz. And then this point here is representing the luminosity observed by Fermi GBM. So as you see, we don't touch this point here because we expect to, this is explained by the magnetospheric flare. So is not to be expected, is not expected to be explained by this mechanism. So what I'm showing here are the light curves produced by the expanding ejecta being powered by the central object. And this, of course, this ejecta is expanding the magnetized medium produced by the central object itself. So it's produced, it cools down by synchrotron cooling, but also by thermal cooling during its expansion. So that's why we are not interested in fitting this point with this mechanism, of course. And so the high energy bands, high energy emissions are down here. You can see that we cannot explain, this is only this, you cannot explain with this part with only synchrotron cooling here, this early, this is the kilonova emission, right? This is the kilonova emission. So what's happening here? We don't have observation at this point, but we have also this rising part of the X-rays and of the radio emission that also Elena showed before. This could be some indication of the, because these are unabsorbed light curves. So there could be some absorption in the material, so I mean opacity. And so this actually, this emission becomes a heating source for the ejecta itself at early times. So if we do that, for example, assume that this matter is not observed, it's not being released at this time, but it's going to heat up the material at this time, we can compute what the evolution, what the thermal cooling of the ejecta would be in this case, in the early part. I'm going to show that in a moment. This is at zoom. This is zooming into this region here, just to show better what how the theoretical model compares with the data around these values. And here you see that. So you see, this is the infrared data, and this is the radio data. You see here that Elena showed also this radio data, and these are the X-rays, and this is already these are already the latest measurements that Elena showed. This let's say enhancement of the X-ray emission that for us is a signature of the emergence of the white dwarf pulsar that you see here in green, because the synchrotron emission, the synchrotron cooling definitely is fading and cannot explain such kind of flattening, which was actually predicted in our, let me go back a moment to our paper. Sorry, because I didn't plan to show that, but it's always instructed to show that. This was our paper 2 years ago, in which we were showing the flattening due to the presence of the white dwarf pulsar, exactly for the values of magnetic field and rotation period that we are finding in our fit here. So then we pass to this region. If we take this as a heating source for the source itself, because of the opacity. And this is the emission. So these are the data points of the kilonova, the AT 2017 GFO data in the different bands. So you see that broadly speaking, the model is catching the general features of this emission, but this model is extremely simple. We are not considering actually a density profile for the ejecta. We are not considering different velocities. This is actually only a two-shell models in which we consider two shells of different mass, just to try to mimic a little bit some density profile and different velocities. Actually, the velocities are roughly the same, and the two shells, one is 10 to minus 3 solar masses, and the other one is 10 to minus 4 solar masses. This is extremely simple model. And is actually I'm surprised that such a simple model can capture all these this structure. So having said that, I will now conclude, mention some salient features of this model. So from gamma ray emission of 10 to the 47 error per second, and the duration of 1 second, observed duration of 1 second, will be produced by a giant flare in the merged magnetosphere. The magnetic field of the blob would be of the order of gigagauss, and the size would be the order 10 to the 9, 10 to 10 centimeters, and expand with a Lorentz factor of the order of 5. The afterglow, the late afterglow, is actually explained by thermal synchrotron cooling, further powered by the newer white dwarf. We see the signature of the synchrotron emission very well in the constant slope, observing the X optical and radio emission. This was one of the points also mentioned by Elena. The recent observed rebrining of the X-ray emission, or the flattening, let's say, of the X-ray is for us is indicating the emergence of the newborn white dwarf pulsar, but of which parameters? So the parameters of the newborn white dwarf are mass of 1.3 solar masses, a rotation period of 3 seconds, and a magnetic field of a few 10 to the 8 Gauss. We as an output of the model, we can compute the energy which was injected by the central object, and this energy is of the order of 10 to the 48 erg. And this is consistent with the white dwarf rotational energy, which is of the order of 10 to the 49 erg. This progenitor, the progenitor of this that form this object, can be constrained to this value, a double white dwarf with components 0.6 and the other one with a mass between 0.9 and 1.1 solar mass. Then the early emission observing the optical, infrared, and ultraviolet, namely the kilonova emission, is explained by the thermal cooling, in which there is a heating coming from the emission, which is reabsorbed by the material. And then we have inferred that the mass of the ejecta is about 10 to the minus 3 solar masses, and the expansion is 0.01 C, which is consistent with numerical simulations of the ejecta of white dwarf mergers. This is this, and then one of the most interesting points is that these white dwarfs with these parameters, with similar parameters to these ones, were proposed by our group in 2012 as a possible progenitors, as a possible explanation of the soft gamma repeaters and anomalous X-ray pulsars, so the magnetars. We have a series of works on that. I mentioned only 2 of them, which were the first one, it was the main idea, and then there is a second one with the first example, which of a numerical simulation of an AXP within this model. Therefore, what we are, since the white dwarf appears to be emerging as a pulsar itself, so we advance the possibility that actually this object, this new white dwarf, could show in the future actually as an authentic SGR or AXP in this sky position. So this is a possibility, a prediction that we are advancing here in view of the similarities of the white dwarf properties with the ones that we were proposing for the explanation of magnetars. And that comes also as these properties of this Fermi GBM point, this flare, seems to be in some sense also very similar as the giant flares of magnetars. So this is, I think this is my last slide. Yes, this is my last slide. So I stop here.
Thank you very much, Jorge. And let's see.
So should I stop the shading?
No, I think I think you could dialogue with Eleonora now. Let's have Eleonora reaction and ask questions, and if everything is clear. I think we should maximize the remaining time, let's say 20 minutes or so, to clarify and to the model and to have questions from Eleonora and you to Eleonora. I think the thing I can see immediately is the different energetic of the two models, but maybe this can come out in the discussion. Eleonora, can you intervene? We have to manage ourselves.
Yeah, so one question I have is how this model accounts for the radio imaging. I don't think this was shown in the slides, but how do you account for the centroid motion that was measured?
Yes, I know you were going to ask this, but not while I was preparing the slides, while you were presenting. No, actually, we didn't include that. And I actually was going to ask you some extra information about that. Because I was thinking, because we didn't attack this problem of the centroid mode. But can you remember which is the Lorentz factor inferred from the motion?
No, sorry, I don't remember. I can check right now. If you take other question, I will check.
No, because I was thinking if there is, let me ask you, the points of the radio emission of that imaging are the corresponding ones observed and let me, around this region here?
I think it's in the earlier data.
Or it's in the earlier data?
Before 1000, I think.
So the radio imaging was taken at, I think, about 100-ish and 200 days.
Yes,
so exactly. It was taken around the peak of the emission.
Yes, we're here. We're here. Because our model can catch very well, you see, all this part. All this part. I was thinking if by any chance, while you were presenting, that this radio imaging could be just the continuity of the flare, that it was expanded from the beginning.
Yes.
Because there we estimate the Lorentz factor could be the order of 5.
Yeah, I think looking at the
I mean,
numbers, I think the
the
Lorentz factor, the estimate is about 4-ish.
About
of course.
4. Okay, about 4. So that's what I'm thinking, that at the beginning we see the flare here in the gamma rays, and then it could show up around here in the radio in the radio with such Lorentz factor. The Lorentz factor seems to be correct.
But before 1000, between 10 and 100.
So that could be a possibility. That could be an explanation for that spot for the radio imaging. There is a question in the chat. 2 questions.
Can you answer?
I don't know who is asking. Maurice Van Putten. In your white door scenario, how do you account for the gravitational wave merger signal observed by LIGO?
Oh, well, that is simple.
Simple, we don't account.
We have this model just solve the GRB and does not look at all to the gravitational wave. And we want to find an independent GRB motivation very clearly fit in the data. And I think the most interesting part on which I return in the energetic, because we fit all this data, maybe you should emphasize more this, okay. The energetic is of the mass of the object, 1.3 solar masses, the spinning period, and of course this pulsar behavior should continue to appear.
That's I mentioned the energy. So we the energy injection was of the order of 10 to the 48 erg, and the rotational energy of the white dwarfs 10 to the 49. So of course the white dwarfs can continue to radiate still for quite a while after this. Maurice Van Putten, but the gravitational wave signal goes up to a few hundred hertz. Needs a neutron star merger.
Yeah, I mean, if you have a white dwarf merger, because white dwarfs are a little bit larger than neutron stars, when they merge, they do not produce frequencies up to a few hundred hertz. Of course, neutron stars are so compact, they easily produce frequencies in their final coalescence process up to a few hundred hertz, theoretically even more, but that's not detected.
Yes, no, that's fine. That's fine. I mean, we are not saying that this system, this merger, can explains that. I mean, we are not interested in explaining that at the moment.
No, but the question I have is, if it is a neutron star merger by virtue of gravitational waves, where do you place the white dwarf merger scenario in that case?
No, not at all.
No.
There is no, there are two steps. One, the assumption of that, okay, you explain. There are, explain the logic, I mean.
Yeah, I'm missing a step here, yeah.
No, this, I mean, the logic, the logic is relatively simple. Okay, we are making a model to explain the electromagnetic properties which are observed. Okay, and I think we succeed in doing that with a white dwarf merger rather than a neutron star merger. So if you try to explain with a neutron star merger, you will see some problems in the explanation of the data. Okay, the current models. If you're trying to unify that.
But wouldn't you agree that the gravitational wave signal indicates we are looking at a neutron star merger rather than a white dwarf merger? That's my starting point.
Well, let me say the opposite. That the electromagnetic emission is showing a white dwarf merger rather than a neutron star merger.
And we don't want to start the discussion about who came first and so forth. I mean,
no. I'm not talking about that.
The data are very clear. There was a signal from Fermi, an integral at a given moment, and we develop a model which can explain the data of Fermi and integral self-consistently with the spectral prediction. Simple. We don't want to enter another political discussion about anything. I mean, we are interested in physics. The data, fortunately, are very clean, the electromagnetic data, And we explain this data. We are not interested in the gravitational wave signal.
Well, but that's, I mean, normally you would take into consideration all the observational data of an event. So
Well,
excluding the gravitational wave data is maybe not the normal way of doing it.
Excuse me, the gravitational wave data, people will have to explain what this data came from and so forth. I mean, there was a problem. It's well known. It's not the problem we address.
Well, I don't know. No, but I think in this particular case,
please.
Yeah, I'm sorry. But in this particular case, we find independently the signal claimed by LIGO by a completely different model independent analysis. So I think the idea that it is a neutron merger is quite firm. And we find it in each individual gravitational wave H1 and H2 detector. So because the signal is so loud. So basically you would have to discount this merger signal clearly present in two independent detectors. That's a tall order. That's my point.
You are right. We discard that signal, and we have some reason to do that. But it's not. Yes, we declare very clearly that if our model is correct, we have to discard the gravitational wave signal. And somebody else approach this political problem and so forth, because that will take, there are people making a profession out of that. It's not our profession. Our profession is we look at the data from Fermi and from, and we don't, and from integral, and we have no intention to discuss the gravitational wave signal because in our opinion, they are not related to the source.
Well, as you know, there is it's a limited, it's like, I think 5.1 sigma association. So if you like, there is a small window, 1 in a million, that these events are not related.
No,
very large.
No, excuse me. But again, we have said whatever is appropriate to say, but I think there is a very big problem about human intervention in physics. And we don't enter into that. We just say we consider the presence of a space-time process, which the future and the past, and human intervention, which has reversed the natural, the official, the space-time coordination, reason not to enter into that problem. It's very difficult to enter the problem of a signal, 5 sigma, whatever you like, where there has been, Pontecorvo used to stress this point. I was always remember Bruno smiling. In this phenomena, he was referring to not to this process, but to a different process. Smiling, he was saying, there is a human intervention. I appreciated more and more this beautiful sentence of Pontecorvo.
Well, that human intervention then should come at the level of the detector, because our analysis is model independent, done completely independently, and we confirm in both individual detectors the existence of this characteristic.
Also, in both the detectors, there has been a human intervention, period. In both the detectors, there has been a human intervention. You know all these things. I mean, go and speak about the glitch and so forth, but this is not the matter I want to speak. I don't want to enter in the glitch and the human intervention. Let's stick to this fact. If you take the GRB 17 or 417 by Fermi and integral, which is a very clean signal, we can explain this as a binary white dwarf, and we predicted a bright spectra and which can express, this is the important point, by our formulation of synchrotron radiation, the observed properties quite remarkably well, going from the X to the radio to the optical. It's not so organ. And we can make even a prediction of what will happen in the future months. Then everything else will be discussed in a different occasion. And
So
there are plenty of discussion.
Yeah. Well, what do you propose to go forward? Wait for another event, for instance, or?
What do you mean another events? We don't have, excuse me, we have up to now in gravitational wave, one event in 1509-14, spectacular, absolutely clear. The only problem is that it happened the first day of the first few days of opening of LIGO. Was never again happened. It's very clean. In analyzing again the physics of that event, we find a difficulty, theoretical difficulty, which we publish with Rodriguez. This is not new because it was the same case which we encountered with the Weber event and the solution by Misner. Misner did a fantastic work of synchrotron gravitational radiation from the black hole in the galactic center. Today, we don't believe any longer the black hole at galactic center. And we prove that Misner made a mistake, and that was the end. In the same case, in the case of 1509-14, we have published a paper in showing that there is a paradox because they were two parts glued together, what we have called in the existence of a mythical man-horse component.
Centaurus.
A Centaurus. I mean, we published, this is published, and this has a difficulty. Therefore, this is very serious in our opinion. And this is what we said today to explicitly to Laguna. And this is the sentence I use at the beginning of the Grossman. Now we are in a situation very similar. We have on one side traditional physics, which is Fermi, integral, radio, X, optical data, clear evidence for synchrotron, which we have been able to reproduce completely, and we have done that, and we are ready to publish also the details. But then we have another set of data, which, as Pontecorvo said, had a human intervention. Personally, and this is a very personal point of view, I discard process with human intervention, personally. And we are not interested. We are only interested to say that if indeed the data of X-ray and of integral and Fermi are explained in our way, there is no room possibility of having the gravitational wave phenomena with human or not human intervention, but unfortunately with human intervention. Therefore, I think our stand is very clear. Everybody can judge. All three events, the Misner effect, the effect of 1509-14, fortunately there are few, 1708-17. We don't want to wait for any other one. The only thing I said this morning is that the quality, unfortunately, of the data, of the recent data, the quality of the recent data of a few days ago are not similar to the clean data of 150914 or of Weber or of 170817. They are not
Oh, but
clean.
those distances were very far out. If 200 some
Are not clean. Therefore, we, as I don't want to use a word of Wigner, or another word by another great man that you will find in the literature, but we have no possibility on this quality of data to establish if the solution is correct or not correct. Actually, in the previous case, the data were good enough to say that the interpretation was wrong. In this case, recent, we are not even able to establish if these data are wrong or not. This is the key point. It's dramatic. It's really dramatic. But this does not mean that we can do good physics. Because when they are good data, we can definitely say if the interpretation of the data fulfill basic physics equation. If not, the data are good, but the interpretation is wrong. This is what I prove on Misner, and this is what we prove on 150914. And we will prove in the case of 170817, fortunately, that the data of Fermi and integral, and of course the splendid data in the Chandra, fantastic data of Chandra. Without Chandra, we will never have dreamed to go back to our model. I mean, it's been uniquely, and this I was very grateful for Eleonora to accept our invitation, because she was the one with the Chandra team to extract this very important data, and they will be even more important from now on. And I have to compliment Eleonora to have done this analysis of the data. It was really fantastically important. The data now are good. And when the data are good, the theory must match the data without violating physical law and without, in my opinion, a human intervention. By definition, a human intervention cancels the validity. Now, I don't want to enter into the story that I heard from Kip Thorne, who told him in the morning the reality, the discovery of 150914. I overheard this discussion of Kip Thorne when we went to Stockholm for the prize of Roy Kerr. We were in the same taxi, and somebody asked Thorne, but how it happened? He said, well, I was sleeping 7 o'clock in the morning, and somebody, he gave the name, called me. He said, we have a signal. This was 150914. And Thorne asked, are you sure that is not an injection? And this person, because Thorne gave the name, and I have I have written all this person said, oh no, was not injected. I am the responsible for the injection. This is what I heard from Tom. Therefore, I don't want to enter this story. This story is very dreadful and is a very tragic story of physics. And I think we have to face the courage to put clear this, which could be very well one of the greatest disasters in the history of physics.
Well, I would still invite you then to look at our paper, because in our independent analysis, we found something beyond the merger. So if indeed anything of a merger was injected, then actually more was observed in the injection. That doesn't seem to be very consistent with human intervention. Actually.
Of course, I will look at your paper like
and the signal that we find post-merger was completely unexpected, actually for ourselves as well, but definitely for LIGO, because LIGO doesn't have the software that has the required sensitivity to be at similar sensitivity for binary mergers. So they didn't see anything. And we do find observational evidence, which we published in this HA letter.
Excuse me, let's do one thing at a time. We are just not entering in this matter. I repeat, and you cannot, I said already. And no, I do not repeat what I said already because it's recorded. If you like, you can go back, but I think the situation is very, very clear. And there is a position I borrow from Pontecorvo.
Well, I mean, on another occasion, I'll be happy to discuss this further with you, because I think there are more issues at play than that you brought up, and maybe that is helpful to this discussion.
Good. Any other occasion will be welcome. Maybe we will have an occasion, as I announced. I don't know if you are in Korea, but from the second, you are in Korea. Beautiful.
Well, if you
at the beginning of August, I announced we have the meeting in a university in a beautiful campus in Korea, and I show today the poster, and I will show again tomorrow. It will be a pleasure to see each other. I don't know if I can come with this problem of pandemia, but certainly now we are experiencing how to have meetings covering the pandemia at a distance, and we will have certainly the meeting in Korea at a distance. The only thing I am sad after seeing the poster is that it's in a beautiful island, which I think I visited before, which is very beautiful. And this is the only sorrow I have, eventually not to be able to come, but I will try to do my best. But anyway, we will have plenty of occasion to speak.
Well, I mean, if you invite me to give a talk, I'll be happy to elaborate on this in any detail that you wish, and then we can compare notes.
Well, I think now we have enough notes from what we said.
May I say something? I want to
absolutely.
Done on this. I will just to thank Eleonora because her presentation was very elucidating for me. So I'm really very thankful.
And let me express the same. I think I have the same feeling listening to Eleonora's presentation. There was a point very interesting, and not one point, many points. But I would like also to say to Eleonora, you have been the hero to elaborate all the data from Chandra. And I expressed that also to a member of our committee, International Organizing Committee. I said, Chandra did really something exceptional, even in this last phase. Fantastic. And she did not realize how your work was important. I will come back to her. Maybe you know who is she. Okay. Thank you again, everyone. And
Thank you very much for these nice words.
Yes. Okay. See you soon somewhere. Where are you these days? California?
Now I'm in Colorado.
Really, I envy you. I envy you. And
very nice.
Must be very beautiful. Maybe too hot. Is too hot? No, not yet.
No, it's just beautiful.
Okay.
Yeah.
Enjoy. Enjoy.
Yeah.
Bye. Okay. This was extremely important.
Bye. So we close the connection.